400 words just come out. It's like a Gregorian chant, you know. It's just, the wind picked up and it was actually impinging on the dish itself. We have, you can see a tagline. They're off to the side. You can't really see them too well. But the tagline that was upwind from where it was being blown was tagged on one of those cement barriers you see on traffic, you see on roads where they put up these cement A-frame things.
Jersey barriers.
They're about 800, 1,800 pounds a piece. There was a rope, a steel cable / rope going as a tagline through a hole in the side of that barrier, that 1,800 pound barrier, and it was dragging that barrier, scaring the absolute crap out of me. I was responsible for this, and I saw my whole life pass in front of my eyes. I just couldn't believe what was happening. Fortunately, it didn't cause any damage. There you can see it's lowered slightly down, slightly more. We got it down. The wind went away. It was really crazy. And here's where it's just about to be sat down. The first 3 layers on the ground are then bolted to all the way around. This is what some of the junctions look like. And here's where everything went wrong. Again. The dome was made by a separate company. There's a lot of moving pieces. Nobody was at fault. No one person was at fault. It's just a bad situation. We worked to make the best of it. This is your tax dollars that we were working with. And it was a bad situation. We did the best with what we had, and we tried to make it work. As it turned out, after we got the dome on, see, we had done testing before we put the dome down. We put the dome down and did testing again, where there's 4 of us sitting in the equipment shelter, and we had pointed it off a satellite. We had pointed it at the satellite, took readings for EB over NO, pointed it off the satellite, turned it up to maximum power, and was measuring everything. And we were sitting there, 3 engineers sitting there, or 4 engineers sitting at this table. And all of a sudden we realized that at least half of the power was disappearing before it left the dome. When all of a sudden we realized this, we didn't know if we were sitting in a echo chamber. We didn't know if we were in a resonant chamber. We didn't know if it was being eaten up in the material that was made up with the dome. We don't know. But literally, when these calculations all hit and 4 of us are sitting there, it's all quiet. Everybody's looking at the computer screen. And all of a sudden, it was interesting. I thought it was very interesting that all 4 of us hit the mushroom emergency off switch at exactly the same time. It was 4 hands that went bam and smacked that thing down, shut everything down. We didn't know if we were dead because of all the power that was being reflected around. And as it turned out, there was a huge amount of power being reflected as a resonant chamber inside the dome. But there was an awful lot being eaten up in the dome itself. It was just a bad situation. Everybody got together, and the company did a lot of things for free. The government gave up a lot of things, and together we got it done. But they literally had to replace all of the pedals in the entire geosynchronous arc for this particular dome. And it took about 8 months. And at the first of that 8 months, I thought, oh my gosh, nobody's going to be using this dish for 8 months. What am I going to use with this? So our son was getting his PhD at Ohio State at that point in time, and I called him. Ohio State? Wow. I thought, you know what? He should surely be able to get a hold of somebody. Unfortunately, you know, Mr. Krause, Dr. Krause was gone long before that, and that the WOW antenna had been moved a long time ago, or a junk, or whatever it was. So there was really nothing that we could do. So I didn't have a whole lot of things that I could do with it, but I wondered if I could, there's a picture of the symmetric pedals, inside look after it was all done. Looking up at the feed point. So that red line there gives you an indication of the frequency range where we're looking. I thought, well, you know, this ought to be useful for something. The problem was I didn't have any equipment. I had 0, I had nothing. So I put together what I had. I I knew what, I don't know, C-band, I'm sorry. I thought I said KU, but it was C-band. This is several years ago. So the down conversion went down to about 125 megahertz center, 200 megahertz bandwidth. I had a Booten millivolt meter. I bought this DATAC device online. I hooked all this up. I had a tough book for my laptop. I recorded the audio for whatever good. I mean, I wasn't trying to be a Jodie Foster. I was just trying to do whatever I could do. I didn't know that any of it would be of any use or any value or fun. It was fun. That was all it was. So these are some of the plots that I got, and all I did was include some of the plots that, as it turned out, rain and weather and daytime weather was a big factor on what you would actually see. But one day, and I would just do drift scans. That's all I was able to do, drift scans to just what's out there. And I didn't even know exactly where to point it, so I would just point it in the direction and I'd see nothing. I'd point it in another direction for the next night. Day after day after day, wouldn't really see much. And of course, this is designed for seeing a huge beacon of RF in the sky, not like it's looking for it wasn't built for looking for quarks or anything else. It was just something that was made for much larger signals. But you notice here the date and the time, and I'll show you the signal. I actually refined that down just a little bit. And that's the signal that I saw one day. I saw this bump pop up and I thought, well, that's cool. I wonder what this is. Well, I don't know. So I left the duct. I didn't move it. I didn't move the dish. I just left it in place. And if you notice, the next day, we're 4 minutes off. I was so happy. I was over the moon, crazy. I was just like, because when I saw that 4 minutes difference and it's the same exact thing, I was just so happy. That was a wonderful day.
A Jansky moment?
That was very much. And I tried moving it a few tenths of a degree, watching it over time. Didn't really change much. On this particular day, I had moved it a little bit. There's a little bit of definition there at the top of the peak. I really couldn't refine it much more than that. Another day. So this is audio, but I think that turned into be absolutely nothing. There's nothing. I was recording the digital, the waveform as well as I had hooked up to an audio recording program. But these turned out to be absolutely nothing. I think they're just birdies in the receive system. Nothing spectacular. I got copies of what it sounded like. I don't know if there's even an audio system in here. Yeah.
Here it is.
What was the bandwidth of your signal that you captured?
200 megahertz.
That was your capture range, but the signal itself was...
Oh, the audio signal. So the audio signal was just, the audio signal was just a 3 kilohertz. Nothing.
You on the spectrum analyzer, what did it look like?
No, I didn't put it on a spectrum analyzer. I didn't have a spectrum analyzer to use on this.
You said you were capturing 200 centered at 125.
That was the specs. So all I know about that is that's the specs on the system itself. I just looked that up in the book.
You hadn't done a G to T test on cassette
Not yet.
before the radar went off?
Nope, not, this was once we found out there was a problem, that's when everything stopped. Everything stopped.
2 minute warning.
I'm all done. All I was going to say was, it was a fun opportunity. It was kind of an opportunity that I'll never have again, and in the end, everything worked out. So.
Is that the galactic center then that you got?
I don't know. I know where I was pointed, but I've never calculated to know what I was pointed at.
What direction was it?
It was, well, I can't, the problem is I can't, the site was classified.
Oh, okay.
So I can't.
He was just having fun.
It was just having fun.
Go ahead and announce what we're doing.
Okay.
Okay, we're fixing to have the colloquium, guys. Other people are going to pop in here, so let's do that. It'll be about your cat, and everything will be great.
Should I open the doors and say?
Open the doors and someone, come on.
So we're taking a picture or not?
What?
I guess we're gonna, I forgot about, we taking a picture or not? How about after the colloquium? We'll do it after, what is that, 1 hour?
Yes. Because this was there. And where are we here? Probably so. Probably so.
It's on. I mean, it's broken up to polygons.
See, North Carolina,
You're okay. That was just the end of my sheet. No. Josh, read. Josh. Yeah, oh yeah, I do it every time. One. Oh, thanks very much.
she had one, we should let's
All right, it is 2 o'clock, so let's go ahead and get started. Our colloquium speaker today is Verice. Verice did grad school and undergrad at Cape Town in South Africa. She was a employee here for 2 years after that, at which point now she is working back at Meerkat and is going to tell us about the Meerkat radio telescope. So please join me in welcoming Verice.
Thank you very much for that introduction. So as Dr. Butterfield said, that I will be talking to you guys today about the Meerkat Radio Telescope, which is a newly constructed radio telescope in South Africa. So I'd like to start the presentation by just giving a quick overview. Firstly, I'll talk about why did the telescope get the name Meerkat? And then I'll go on to where is Meerkat located. We'll look at what constitutes the Meerkat radio telescope, and then we'll look under the hood to see how Meerkat actually processes the data from space. And then we'll look at some science with Meerkat. So, why Meerkat? So, originally the telescope was going to be called the Karoo Array Telescope, and that stands for CAT. But then it got extended, so originally there was only going to be 20, and then it got extended to 64, so then they called it Meerkat, which translates, so in Afrikaans, meer means more, so it translates into more cats. But at the same time, it's a very, very cute mammal called the meerkat that you can find around site and other places in South Africa as well. And you guys can try and pronounce that scientific names. I definitely can't, like suricata. So where is the Meerkat Radio Telescope? In short, it's in the middle of the Karoo Desert in South Africa, which is a place with stunning sunsets. So as you can see in this photo, it's spectacular sunsets. But also Google knows where Meerkat is. And this is a map of the southern part of Africa. And this is an outline of South Africa. And this red marker is where the Meerkat Radio Telescope is located. So the South African Radio Astronomy Observatory actually consists of multiple sites, of which Meerkat is located there. And it's also located in a radio quiet zone, which has a radius of about 70 kilometers around the core of the Meerkat Radio Telescope. And right here at the edge of the radio quiet zone lies the small town of Carnarvon, which we have as SARA offices. We also have offices in Cape Town, and that is where I am based. This is also where the main Meerkat control room is located. However, there is a small operations control room at site as well. Then up in Johannesburg, which is close to Pretoria, we have the Hartebeespoort Radio Telescope. And that is the telescope that was built way back in the 60s by NASA, and it was used as a communication downlink station for the Apollo 11 mission. So the Hartebeespoort Radio Telescope also now forms part of the South African Radio Astronomy Observatory, and there's offices in Johannesburg as well. So if we zoom in a little bit more, we can actually see what the site looks like, but you guys can see that this is an outdated satellite image because there's no dishes actually up there. However, you can see the locations of the individual Meerkat dishes. So over here is the core of the Meerkat telescope. It's an area with a diameter of 1 kilometer. And there's 64 antennas, and 75% of the Meerkat dishes are located within this 1 kilometer diameter. So that's 48 of the dishes. Also in this picture, you can see the Cat-7 precursor radio telescope. Well, you can see the location of the Cat-7 radio telescope, which is the precursor to the Meerkat radio telescope. From Cat-7, there's a road that goes up to this circular area, which you guys can see, and that's the location of the SARA radio telescope. This is a road that comes in from Carnarvon, and this is the Losberg site facilities. It was named after the Losberg. So this mountain is called Losberg. And we'll look at the Losberg facilities a bit later during the talk. A baseline is defined as the distance between two of the dishes, and Meerkat has a maximum baseline of 8 kilometers. So that means that the furthest distance between any 2 points of a Meerkat, between any two Meerkat dishes is 8 kilometers. So just as a side note, and in case you guys were wondering what these other telescopes that I've been mentioning looks like, this is the Cat-7 precursor to Meerkat. And down here we have the Hartebeespoort radio telescope, which is situated, so this is the telescope that was used during the Apollo mission. This smaller telescope up here is actually the precursor to the Cat-7, which is again the precursor to Meerkat, which you can see here in the distance of the hydrogen and copper reionization, the SARA array. And the reason why I really want to show you guys this, as I'm sure you know, is that the SARA prototype was built out here in Green Bank. So what is Meerkat? Meerkat is an interferometer, and that means that it is individual radio telescopes that gets combined in order to form a larger dish. Meerkat is also a Gregorian offset antenna, So here you can see the main dish. The main dish has a diameter of 13.5 meters. It has a pedestal, it has a sub-reflector, and it has a feed indexer. So the astronomical sources comes from space, goes to the main reflector, gets reflected to the sub-reflector, and then to the feed. The slew rate in the azimuth direction for Meerkat is 2 degrees per second, and it can turn, so it's like 0 is in north, and then it can go to negative 180 and then to positive 275 degrees. It can, the slew rate in elevation is 1 degree per second, and it can go all the way down to 15 degrees and then all the way up to 88 degrees. Each antenna is about 19.5 meters tall and weighs 42 tons. So the rotating turret has 4 receiver slots. L-band has been fully installed and is operational. UHF band, all the receivers have been fitted, and 58 of the digitizers has been shipped to site, and like the installation process is ongoing. And the S-band receiver is also, deployment of the S-band receiver is also underway. We are also exploring X-band in the future, but it's not in the budget for this financial year. So all of the radio frequency all the RF signals are sampled at the feed, and this is a zoom in of what the feed indexer looks over here. So these are the receivers. The job of the receiver is to take is to collect the radio signal and convert it into an electrical signal, which is an analog signal, and that analog signal gets sent over a coaxial cable to the digitizer, which is the unit that is responsible for converting that RF signal into a digital signal. The pointing accuracy of the Meerkat is 25 arc seconds, and the base pointing accuracy is 5 arc seconds. The total connecting area of Meerkat, so let's do that calculation. So it's 13.5 meters for one telescope. That gives you 143 meters for area for one telescope, and then that times 64 is approximately 9,164 square meters for the entire array. Construction of Meerkat began in March 2014, and the telescope was inaugurated in July 2018. Each of the dishes were assembled on site, so they couldn't be shipped as they are. There is a shape that I will show you guys a bit later. Each dish consists of 40 aluminium plates, and they're fitted onto a steel framework. Once the dishes has been assembled, they get transported on this abnormally large truck to where the Meerkat is located, and then it had to be hoisted using a crane. So this is the Lost Branch site facilities. Over here you can see the shed in which the panels were assembled. I actually got to see the very last dish being assembled. I was on site during that time. It was very exciting to see the last Meerkat dish being assembled. This is the diesel tanks on site, and this is staff facility, housing containers. And this over here is the Peru Array Processing Building, which is the Faraday cage that houses all the electronics on site. During the inauguration, there was a small model of what the interior of the KNP, the shielding room, looks like. So you can see the honeycomb structure over here. This building is also built into the ground, so it's approximately 1 story level into the ground. And you can't see it in this picture, but there's a heap of ground that also provides another 20 dB of shielding for the telescope. So next, Now we can go to the next section and we can look under the hood of how Meerkat actually processes the data. And in this section, we'll give a system overview. We will look at the L and the UHF band receivers. We will look at the time and frequency reference system. And we will look at the digitizer units. And then we will look at the correlator beamformer. So this block diagram gives an architectural overview of the telescope. You've got 64 inputs and you can select, so this is on one antenna. So you've got the receivers and you've got the digitizers and you can select either UHF, L or S band. This goes, after it's being digitized, it gets converted into an optical signal, also in the digitizer units, and that goes to the receptor switch. The receptor switch then goes to the fiber patch, and this is where the signal gets transported to the Peru array processing building via fiber, which is buried 1 meter under the ground for temperature stability. Once the signals gets to the Peru array processing building, all the data gets plugged into a 40 gigabit Ethernet switch. An F engine is the fast Fourier transform. This is the unit that channelizes the data into different frequency components. The X/B engine, those could, like an X engine is the correlator and the B is the beamformer. There's also user-supplied equipment, and user-supplied equipment can easily integrate with Meerkat because we make use of multicasting. The following data streams are also available for the user-supplied equipment to subscribe to. So if you've got used equipment, it can subscribe to the raw data coming from the digitizers. It can also subscribe to the F, like it doesn't have to subscribe to the digitizer. It can decide to like take the data from the F engine, or if it wants to use the data from the X or the B engine, it can subscribe to that data. The data products from each of these processing nodes are packetized as speed streams. Speed is the streaming protocol for exchanging astronomical data. And now that we've looked at an overview of the system, we can go have a better look at the different subsystems. So this is what the L band, this is an L band receiver, and this is what it looks like in the lab. It's got its protective dome removed here. And this is the front view, and that is the back view. These circles are called concentric choke rings, and they form part of the waveguide of the receiver. If you add or remove some of these, you actually change the beam pattern of it. And the dipoles, which you guys can see in these pictures, they actually sit right behind the feed. So this is the part that picks up the signal from space. Meerkat has been optimized for having a low side lobe level. So when you look at the radiation pattern of any antenna, you know, it will have side lobes. So you will have your main lobe, and then you've got your side lobes. And the relative difference between the main lobe and the second main lobe of the L-band receivers is 26 dB. The bandwidth of the UHF band receiver is 580 to 1010 megahertz. And for the L-band receiver, it's 900 to 1670 megahertz. Did I get that right? So I said UHF band first, right? Okay, great. Okay, here's a block diagram of the L-band receiver. So you can see the dipoles and the ONT, And you've got vertical polarization going to one low noise amplifier, and you've got horizontal polarization going to another low noise amplifier. The receivers make use of two-stage cooling. This part is kept at 20 Kelvin, and the second stage is like room temperature. The calibration source sits in the second stage, and that is a noise diode, and the noise diode gets controlled by the digitizer. So this graph shows the receiver temperatures, noise temperatures. So this graph is like measures from the lab. The system noise temperatures when the antenna is fitted onto the telescope is 22.5. So for each polarization and their combined average, the system noise temperature has been measured. So next I would like to tell you guys a little bit more about the time and frequency reference subsystem. So this is the subsystem that provides timing to the telescope, and it also provides the pulse per second for the telescope. So we have two hydrogen masers provided by T4Science, and the time and frequency reference group consists of the Carew array timing system, the sample clock generator, and the pulse per second transmitter. So there's also a timing master controller, and the timing master controller is in charge of calculating KTT, which is the Carew array telescope timing. Carew telescope time. The CATS system is the system that's responsible for measuring the round-trip delay to the antennas and to accurately timestamp the data. So there is a signal that gets sent from the KAPB building to the antenna, and then it gets reflected back. And that offset is measured and then used to accurately timestamp the data products. The hardware that gets used in the time and frequency reference subsystem is the two hydrogen masers. Then we have Septon Trio GNSS receivers connected to the masers. And we also have two rubidium standard GPS clocks. And all of these clocks get combined in order to form KTT. So next up, I've got the UHF and L-band digitizer. So this specific picture is of a UHF band digitizer. And I would just like to remind you guys that at this point, the signal coming in is still an RF signal. So over here, you guys can see the SMA connectors, and this is the connector for the optic fiber. Because the digitizer units sit right up at the telescope, we really needed to make sure that it doesn't emit any RFI. So all the electronics is inside an RFI shielded box. And in turn, these RFI shielded box is in an RFI shielded box. So get this right. So over here is the RFCU. That is the radio frequency conditioning units. That's the units that contains the anti-aliasing filters. And these filters are important because Meerkat makes the use of bandpass sampling. So the anti-aliasing filters need to have nice and sharp edges so that none other interference gets sampled down into baseband. So that's the use of the anti-aliasing filters. So we've got RFCU for the H polarization and V polarization. Then we have two sampler units. So those are where the ADCs are actually located. And you can see the fiber units coming out here to what is called the D engine. This is the unit that packetizes the data, which takes the optics data and packetizes it into the speed format. And then at this point, it's 10 gigabits per second Ethernet times 4 that goes into the antenna pedestal. And then from the antenna pedestal, it's a 40 gigabit Ethernet link that goes to the Peru array processing building. So data rates. It's 10 bits times 2 polarization. And we sample at 1,712 megasamples per second. So that produces 34,240 gigabits per second per antenna. So that's the digitizers. Let me just make sure that I said everything that I wanted to. For the electronics group, the digitizer unit is fitted with a Kintex 7 FPGA. So next up, I just want to give a quick overview of our correlator beamformer architecture. This block diagram shows the interface between the digitizers and the processing nodes. So for Meerkat, the processing nodes are SCARA boards, and SCARA boards are FPGA boards. And recall from the previous slide, I said that there is 34,420 gigabits per second from each antenna. So times that times 64, it produces 2.2 terabits per second. And all of that data gets plugged into multicasting switches. So there's multiple switches which this data plugs into. So the processing nodes, they can are scarabs, and a scarab can be configured to be either an F engine or an X engine or a B engine, and it can do this because of the field programmable gate array FPGA technology. Scarab is fitted with a Vertex 7 FPGA, and this is a picture of the Scarab boards. And yeah, it's like, so the FPGA is underneath the fan. So for the F engine, there are 3 frequency granularizations that Meerkat currently implements. There is the 1K mode, the 4K mode, and then the 32K mode. And Meerkat can also form subarrays. So this means that you can split the 64 antennas into different subarrays. You can have, for example, one 16 antenna array doing holography and another 16 array doing software tests, and that other 32 being used in 32K mode. So over here, this is a picture of what the Peru array processing building looks like on the inside, and you can see the Scarab racks over here. In total, there are 288 SCARA boards. We have 54 Mellanox switches. Each of the Mellanox switch has 12 40 gigabit Ethernet ports. So next up, science with Meerkat. So Meerkat has many large survey projects, and I'll only be covering a few. We also have telescope open time, and we've received about 25 proposals this far. And in this section, I will be talking about the UV coverage for Meerkat. I will talk about some science projects for Meerkat. I'll talk about Meertime, and I'll give an overview of a recent discovery that was made with Meerkat. I'm just going to grab a bit of water. Any questions so far? Are we doing questions afterwards? Yes, Paul.
Are we doing questions after?
How would you guys want to do it? Afterwards?
Is that your question?
Okay. Yeah, maybe I should finish off the science and then we do questions afterwards. How does that sound?
Great.
Okay. So an interferometer like Meerkat has a synthetic aperture, and this synthetic aperture is called UV coverage, so UV. The UV coverage is dependent on the number of antennas in the array, the configuration of the array, the frequency that you're observing at, the declination of the source, and the length of your observations. So remember, like at the beginning of the talk, I talked about baselines and how a baseline is the distance between any two telescopes, well, any two antennas in the telescope. So for each baseline, at a specific point in time, you get one sample on the UV coverage plane. And Meerkat had, the calculation for the amount of baselines is n times n minus 1 divided by 2. So for Meerkat, that is 2016 baselines. So that is 2016 points on the UV plane, and then as you observe for longer, it creates these tracks. So this is for an observation of 8 hours long with a source declination of negative 30 degrees. So science with Meerkat. As I mentioned, we have a lot of large survey projects, of which Thundercat, TRAPPIST, Breakthrough Listen is a few. MeerLift is not Meerkat science, but I'll tell you guys a little bit about MeerLift, and you will see shortly why. But let's start with Thundercat. Thundercat is the hunt for dynamic and explosive radio transients with Meerkat. They study high-energy astrophysical processes which emits radio transients in radio bursts. So amongst other sciences that they are wanting to explore, here's just a few that Thundercat wants to explore. It's galactic jets from accreting objects. They are looking for radio counterparts to X-ray binaries. And they're also looking at supernova and gamma ray bursts. Then TRAPPIST. TRAPPIST is the transients and pulsars with Meerkat. The TRAPPIST group has installed multiple CPU GPUs in the KNEB building, and this system can form up to 400 beams on the sky. Amongst other sciences, what they are looking at is they are looking for pulsars and transients in supernova explosions, pulsar wind nebula, and Fermi gamma ray bursts. They are searching for pulsars in globular clusters, and they're looking for pulsars outside of our galaxy, and they are looking for exotic binary pulsar systems. Breakthrough Listen uses Meerkat in commensal mode, and they've recently installed all the Breakthrough Listen user-supplied equipment in the Karoo Array Processing Building. Breakthrough Listen is running the largest survey in the world to look for life outside of our planet, and they also make use of the GBT in order to conduct this survey. So MeerLift, I wanted to talk to you guys about because it's an optical telescope that was constructed by the South African Astronomy Observatory, our sister organization. It is located about 250 kilometers away from Meerkat, and it will track whatever Meerkat is looking at. So whenever there's a transient, and when it's nighttime, and the transient was discovered by Meerkat, we could see what the optic equivalent of that looks like. It's a 0.6 meter telescope. Mere time. So, mere time means I need more time. Mere time is a project, and it's the key pulsar timing project for Meerkat. And these are just some exciting results from recent near-time observation runs that happened. But near-time has various science cases as well. It has the timing of 1,000 pulsars per observation. It's timing pulsars that's found in globular clusters. It's using pulsars in a pulsar timing array in order to try and establish what the gravitational wave background noise looks like, and gravitational waves that can be detected by pulsar timing arrays are in the order of microhertz to nanohertz. There are also timing binary pulsars, which this is an example of a binary pulsar that was timed. So on the left, you've got J1644 minus 4559. So you can see the sharp profile of the pulsar. And on the right, you've got the binary pulsar, which is J1757 minus 5322. Now, for the recent discovery that was published in the Astronomy and Astrophysics manuscript of July this year, SARA et al. Found neutral hydrogen gas within and around Fornax A, whilst working on their large-scale survey project titled a Meerkat survey, H1 survey for Fornax. So they found neutral hydrogen gas, which are these green blobs on this picture, and these arcs are just shown to aid the eye so that you can see the hydrogen tails. This image is an optic overlay, so the green blobs is the radio image and the image in the back is the optic image that was created by the Fornax Deep Survey using the Omega Cam on VST. So VST is the VLT Survey Telescope at Paranal Observatory in Chile. The paper is titled Neutral Hydrogen Gas Within and Around NGC 1316. And I have that paper if you guys want to read it, if anybody is interested. And lastly, here's an image of the center of our galaxy, the Milky Way, that was revealed at the inauguration in 2018. This image is a 2 by 1 degree portion of our sky, and it corresponds to an area of approximately 1,000 by 500 light years. The image shows star-forming regions, remnants of supernova explosions, and radio filaments. This white part over here is the galactic center. This image was created by data taken from Meerkat as well as the GBT, and they were combined in a process called feathering. The red parts is the lower, is the not, you can't say not so bright, but like it's the yellow ones are brighter, and then the white part is the absolute brightest objects in this image. And I would just like to take this opportunity to also thank Dr. Armentrout and Dr. Butterfield for organizing this colloquium, and Thomas Chamberlain for hosting me, and everybody else who made this trip possible. Thank you very much. Questions for our speaker?
Reese, could you talk a little bit about what your role is in all of this?
Sure. Just let me grab some water. So I'll use the slides to do that. Well, I've worked on the digitizer master controller, which is the software that communicates and controls the digitizer units. So back when I started at Meerkat, that was like one of the first things that I got to work on. And that entailed writing sensors to monitor, for example, the temperature, as well as the speed protocol that I mentioned to you guys about. The digitizer sends speed packets over the optic fiber, so I wrote some of the speed code that is implemented for the digitizer master controller. At the moment, I am working on the TMC, which is the timing master controller. I'm working on software that combines the different hardware to produce KTT to UTC like currently we are tracking to GNSS, but the goal from Meerkat is to be able to track the timestamps to UTC. And that's the software that I'm currently working on. Yes.
So your multicast switch, I think you said, is somewhere around 2.1 terabytes of data that it's processing before it multicast?
So the multicast switches, there are 54 of them, and they just kind of route the data. So they don't do any of the processing.
Right.
Yeah, so the 2.2 terabytes that's coming from the telescope is not actually all on one link. That's just the total of all the
Right.
different ones. Yeah.
So those multicast switches, did
Yes.
you commercially buy them or?
Yes, they're Mellanox switches.
Oh. Okay.
Paul, you had a question?
Yeah, the beamformer coordinator, you mentioned FPGAs, is that, are you also using any CPU or GPUs?
So the Meerkat correlator beamformer doesn't specifically make use of CPU, GPUs. That is all SARA based, which is FPGA based. And it internally has a microblaze CPU for control, so which is called like a soft door. Does that answer?
Yeah.
Yes.
Hi, my name is Ed McCauley. I was one of the original folks at Xilinx. So I appreciate you using all the Xilinx points. My hobby interest with SARA is Earth rotation aperture synthesis.
Okay.
So I'm curious about a couple points of your early block diagram. It looked like you could do correlation in both the time and frequency domains. Is that correct?
We don't do any correlation in the time domain as far as I understand. So as far as I understand that the correlator subscribes to the F-engine data, so that's in the frequency domain. But in theory, that is true, and we have user-supplied equipment that do subscribe to the timing data, and then on CPU, GPU do their own analysis.
Since you're part of the timing the creation or orchestration, with what resolution are you injecting your timestamps? No, how many nanoseconds, femtoseconds, how accurate are your timestamps?
The specification is, I think, to within, so the uncertainty with which KTT to UTC is 5 nanoseconds, but that is not implemented yet, like because I'm still working on it.
Is that a little bit of
And like
information?
it's still in progress, yeah. But like I think at the moment it's to within 100 nanoseconds, yeah. But it needs to be better.
Well, what is the resolution of the timestamps relative to your local standard?
I don't know if I understand the question, sorry.
Irrespective of how close the local standard is to the rest of the world. When you
Yes.
timestamp, when you've got a digital stream coming out,
Yes.
how precisely can you say it was sent?
Yeah, so it's supposed to be within 100 nanoseconds of 5 nanoseconds of UTC, the uncertainty on that.
That sounds awfully gross.
With the correlation.
I think they're talking about the skew between the various sampling points, not between absolute time, but between all the different radio telescopes. You have to have some time accuracy between them. And it doesn't, you don't care where they are relative to UTC within reason, but within each other they need to be very, very close. What is that number? I think is what they want to know.
Oh, okay. I think if I understand the question correct now, that's what the CATS system is supposed to be doing. So it measures the round trip delay, and then I don't know the number, like I don't have a number for you, but
Well, let me put it a different way.
Yeah.
When you generate a packet of sample data, you've got some metadata that says it occurred at such and such a time. What is the least significant bit of that metadata in time?
I don't know. Like it's like a 64-bit timestamp.
You know, but what is the rate of that timestamp?
Oh, the rate of the data going through. Maybe we can take it offline and draw some
Sure.
pictures and stuff.
Sure.
Yeah, sorry. And maybe you can sit in, because I don't remember.
Thanks, Chris.
And maybe I don't know the answer. Yeah.
I'm just curious about any other science results that you may have heard about. Different result, with regards to like the FRB survey, Pulsar survey. Is there anything about stats that you can say?
So near time is up and running. So when I was at the IPTA, there was about 13 successful near time runs that has occurred. By now it's probably 15 or more. So that's an ongoing process, and I can show you the images again. But like, I don't know if there's any new papers that have been published.
You said that there were something like 25 proposals in. What does the proposal process look like for Meerkat?
I
Do
don't
you
know.
Okay. I can look it up.
So those 25 proposals that I mentioned, they were the open time proposals. For the large survey proposals, there were more. I don't know how many there were. Yeah. I can put you in touch with somebody that would know how the proposal works.
So as you're very well aware, in Green Bank we have a beamforming receiver that is also sending raw digitized data over fiber, and we've had some issues with that process. You guys, is it a similar process for Meerkat, or is it digitization? Are you having to recover, the byte lock and things
No,
like
so
that?
it's a different process.
Okay.
Yeah. We packetize the data at the digitizer.
Okay, so it's actually packets over the fiber.
Yeah,
Ah,
yeah. So
okay.
it's I don't think I ever said this, but yeah, it's an IF signal that goes over the fiber.
Those packets have a header
Yes.
that has all sorts of interesting information.
Yes. So it's
That's what I'm trying to nail you on, but I do that.
Yeah, we can. Like, I would love to chat to you more about it, because I could, and if I don't know the answer, I can definitely point you to somebody who would have the answer. Yeah. Yes.
Could you comment briefly, I know we're running out of time here, but on your breakthrough listen, can you comment on the general strategy of that portion of the project?
So the way that I understand that breakthrough lesson works with Meerkat is that it plugs into this switch. This would be a better picture to have up here. So basically, this used equipment, the user supplied equipment, that is basically one of those machines would be breakthrough listen. Well, not one, they've got multiple CPU, GPU processors, but it plugs into the 40 gig switch, and then it can subscribe to any of the data products. And I think that they observe while other observations are also taking place. So they benefit from other science. So they can use that, they can also subscribe to the data, and then the data gets routed to their machines, even though it's not their dedicated section. Does that answer your question?
Yeah, that's good enough, thank you.
Dave McMahon is around. You should speak to him. He will be able to tell you much more than I can.
I am interested in hearing about your quiet zone.
So the quiet zone has a radius of 70 kilometers from the core. It's about 15,000 square kilometers. We also make use of the different tiers. Like once you get into this zone, there's no more reception. Once you get into this zone, you should switch off your phones. So it's very similar to what the GBT and GBO makes use of. But other than that, I can't tell you much more. But I can definitely put you in touch with people. Like we had this brochure that explained a
So it's a federal law?
Yeah.
So how many people got caught?
In the radio quiet zone, there's like nobody. Yeah, like it's a very, yeah, there's not a lot of people there.
It's quiet because nobody wants to live there?
Yeah, it can be a very harsh environment. Like in the winter it gets really, really cold, and then in the summer it gets really, really hot. Yeah.
So you're not dealing with civilians complaining?
Oh, they always complain. So I think some people think that it's our fault that they don't get Wi-Fi in their town, but like they wouldn't have had it in either way, because it's not like we took anything away.
Yeah.
Yeah.
Bob and I were wondering what the most dangerous animal.
Yeah, snakes. Actually, you said snakes. We get like other. Yeah, there was a puff adder in one of the. I don't know how it got in there, but like it was in the pedestals, like in one of the meetings that we had. There's a picture of it. Yeah, so when like somebody opened up, like there's a door at the pedestal. When somebody opened it up, there was like a puff adder there.
That is so scary.
Yeah.
So who eats meerkats?
Yeah.
All right, any final questions for speakers? You mentioned that there's a control room in Cape Town, and I wondered how the data gets there.
So there's a fiber link from
All the way
the
yeah.
site. Well, there's breakpoints at different places, but yeah, it's over like a high-speed fiber.
So you
And all the
realize-
data goes to Cape Town.
Is it fiber that was already there, or did the observatory generate it?
I think the observatory had to lay it, but I would need to fact check that. Well, definitely like on site, like the fiber had to be laid, but like the link from Cardinal to Cape Town, I'm pretty sure had to be laid. But yeah, I can't say with certainty. Yes.
If you're done with the technical discussion, can you go back to your Google Maps slide? I'm curious as to what those big brown things were on it.
Yeah.
Those things.
Oh wait, these things?
Yeah.
Those are mountains. I actually like climbed this mountain and ran all the way over here. This is about like 10 kilometers. Yeah, so you go up this mountain and then you can run all the way across and then along to antenna number 63, and then there's a road that goes over there. And then these are also mountains. So they're all really flat. So in this picture you can actually see a bit better what they look like from the front. So that was the top view, and this is like a side view.
Like a nice.
Side view.
So what cut the tops off?
The Lorax.
Are they volcanic formations with a crater?
I don't know how the Karoo plate, the Karoo tattoo originated. There are some volcanic rocks now that you mention it that some people have like explored, but I don't know the complete formation of it.
All right, any last questions for our speaker? All right, let's take.
You slept through too much of that.
Yeah, it's on the
you still want to talk about,
all sorts of stuff.
It's like, for the people that sign to it.
Like the big things for publication, that was published, but that talks more about like, not the sign the results, it's just like what they're gonna do.
Offering, discuss also. It actually talks about
Like there's just some things that I want to see how people
you use, patterns, power
No, listen, the large meeting is not the place to nail down that. But if you've got some time to sit down and like the figure, let's start with getting time to each antenna. With what uncertainty? Your internal time. Again, I don't want to get into discussion.
So basically what happens is that each antenna has its own time that gets referenced to the same antenna. So they should always sync
Frequency is easy, but getting the time complicated.
Thank you.
So the precision, what is the precision of the time in that? What is the significant I had fiber optic 2 watts. That was some nanosecond uncertainty. So assuming
It has to be like a really small number, because like otherwise you won't be able to. Yeah.
So we're not talking about 5 or 6. We're talking small. So,
I remember.
yeah.
I wasn't sure.
Somebody's going to sell people, so yours is available, that's what we've been using.
Yep.
I know. Or the way we did it, we put a header on each packet. But the question is, what is the decision? What is the uncertainty
But it's
about
old
that
enough.
header information?
But the valleys are still contained.
Okay, you wouldn't be getting that risk. Is that the preferred way to do it? That's what I think. That's the way to do it.
It's an order of magnitude.
Also powerful, it's file.
Based on television.
Yeah, but that's talking about the uncertainty
Of the ATT.
Yeah, and I don't care about that, that's a whole separate issue. What I'm talking about is when you create beamforming with digitized data, how close is knowing when that clock transition occurred at each node? And how do you get that metadata? Tricks to put in that metadata that has more resolution than obviously the signs between each sample.
How long you stay silent?
That's a strong that's not last, this is lacking on that. Integration of curiosity, publisher person, because I was just like, the system just ignores me. He wants to come over and wants me to pet you. Well, right, his is all stuff. So what do we have next? And the cat's nose was all over inside the press. We're interested in that, there must be something bigger. Where's the food? Where's the and then the cat was
Now you risk that everybody's scattered, you might not get less.
I think here's the solution to the problem. This is what you need.
Can they make it look like you were actually there?
You take somebody else.
Hey, did you see that? I didn't see that. You know, we all have breakdowns on them.
What's that making that squeaky? See that? Is that something that you see? Yeah.
About that, is that you?
Sure, but it's a frequency range.
They're very low, so it's 3.73. So we essentially use they got autonomous. More nose prints on it?
Yeah, that's right. The cat actually,
Two sets of software.
Well, it's definitely a recycled box, and it has 10 times the volume needed. However, it was available, really nice use. That's a pretty rugged meter is a problem. Meters go work afterwards, so yeah, that's hard to believe. It was originally nitrous oxide, where we had EPA scrap that was sticking on it. I was kind of wondering where that came from. So they had a nice box, they got a nice meter, and maybe it's, this, I like the meter box a lot bigger than I wanted, but I said, well, the meter's already out of work. Making a hole for a meter like that is a lot of work. And this box already does a hole for a meter like that. Really small round dice for controls, easy to kind of big with the speaker, opening wasn't too bad. But I don't want kind of precision square about big. Just way too much work. Oh, you just hear it. Some of the people see what look at as part of the in this crowd, yes. Yeah, and other crowds, not really. Yeah, very good. Kind of box. Does all the calculation and checks. A little ritual to go through the back, because it's all the board for the, Arduino was in the back, and I wanted USB to be available. So, it brought the board through some of the there's half service assets.
Thank you so much.
That was great. It's nice to meet you.
Because I mean, if it's not for something that
that one is big enough that it can blow the fuse without hurting the diode. So I got the diode just shut across the fuse and see it was knowledge base. Definitely has some kind of abstract word for crudeness things like useless construction. What is wireless? Just curious about sockets you can extend together. Do some of that. It's an easy way to put all your modify stuff. First I started playing with it, I put it on the chest and covered it with my hand. And I went to move it later to the front and I said, that's not coming off the board. So I just threw another encoder. And the encoder actually I've bored it out because I'm constantly changing the level thing when I'm working with a signal generator in the lab. And I actually bored the encoder out. So when I bought a new one, I bought one to have that greater life cycle operation. So it was $1.79 instead of $1.59.
For the sample. Sample box.
It's a little detector board there. That's a homemade IST back when I put the power in. And then when you're going to see the signal generators and stuff like that, you really don't want mustard and so I pulled this little wire off here, and now that power is the power. The order for some of the power over bias, put it there, and this is like 12 volts.
Well, it's good to see you.
Yeah, thank you so much.
Are you leaving tomorrow as well?
Yeah.
They're supposed to get construction.
So do you have that?
I'm going to go to, well, I'm here till Friday, and then we're going to go camping.
You missed the earlier one?
Yeah, so excited because it's like a place that we used to go to when I was living here. And it's St. Mary's out in Virginia. It's so beautiful. There's like a rock. Yeah, I'm so excited.
Boston for me. Yeah, test software, change signal inputs, but rather just put something in the model. Thank you very much.
Hey, so I'm back in the truck. Oh, thanks. You know what?
So all of us are interested in that process, because I played with just a 2-antenna launcher in my backyard. So I kind of sort of understand the process, but still you look at all that.
Yeah, same,
The antennas, well, the 2 antennas are seeing, right? But you get hundreds of antennas. It is a substantial job. So are you mainly the computer person on this? Or the computer science person or an astronomy person? Both. Okay, so you're a computer person.
Yes.
You're a computer person that has become interested in astronomy, but an astronomer that's become interested in computers.
Okay. Yeah, we had our, when I was in college, we were in 20.
Okay, yeah, we'll probably publish in our journal what comments you have. So I cruise through this group can tell me how to do this.
You know, they mentioned, like, that's not mine, like, mine's like a HDMI-C to HDMI, but I should just double check that I got my cable.
Yes, if you leave any interesting computer pieces here, we'll just take them home with us.
No, it's just like a one, like, but I need to share.
I'm already set up on this laptop. I just have some of these around, so it's okay. Most people like it.
Sorry for the hard question.
No, that's good, like, but I am gonna try to look into.
It's a good way.
What you need?
Yeah, it's recorded. Yeah, I can talk to guess about making sure that we can it was recorded.
So the red cap.
Right here it is. It's over
You
here.
give everything to Ann and let her know that Sarah Group wants it. She'll make sure everybody gets it. That way you have one contact. And Sue Ann ties everything together very good. If you want something done properly, you trust Sue Ann.
Big up.
Where is your... I've sort of been parking in this stuff.
I said, I'm sorry about that.
Well, it's not like it's
I don't want to say, like, I don't know. Like, I mean, I've seen like the pulsar, like that was like many entities, but like, it could potentially go lower.
We go our.
I'll send that, send the PDF to Suzanne, and then if you ever have any questions, my email address is on there, I will answer it. Like, I'm just-
Bruce, if you want to start a little early, you can. I don't care to me. If you want to start about 3:20, you can. Let's just do super progress. Thank you. 3:19 or so.
Thank you.
Yeah, thank you.
It still goes in the presenter. Okay, just use the space bar. Either way, yeah, laser for you, around the bar. Yeah, it's white activities.
Are we going to have right after? Yeah. I don't officially have it, right? Well, we got it.
I think the one that I took, it's strawberry, and when I close and cut it, the protects it, except push it. So the battery, as soon as you empty your battery, as soon as it's empty, it starts leaking. I was at first I thought maybe we could just there was this everything is coming. I don't know if it's even So what's his name?
That's what?
The cat's name.
She's Stripes.
Cheese Stripes?
Yeah.
Oh, good.
And she's been a great lab assistant most of the time. Occasionally knocking a few things over and stuff, but, yeah. That's
Well, you didn't need that.
Not get any further than the computer.
Yeah.
Family. It was just curious from
Anytime I am poking anything, the cat, it's just yeah.
So you're
It's definitely got the curiosity. It knows it's always in there.
What's all this crap?
Yeah, I don't know, but it's always got to check it out. And once it even brought me what I thought was a solution to my problem. I was working outside, poking the sun noise, tree noise, the sky noise, and taking some measurements. The cat's watching me. All of a sudden, the cat disappears out of the brush and comes back with a big rat. And drops it at my feet. Here's your solution, guy.
And surprisingly, it was the solution. Maybe she was telling you that you were hungry, you didn't quite realize it, and you should stop and eat.
Stop and eat a snack, maybe, just have a little disagreement on what's
Stop and give me some attention.
I'm sure stop was a part of that message.
How long was that out there?
Anytime I'm outside.
No, I mean that it found the rat and came back.
Oh, it's like only a minute or two.
It was like,
it looked at me, and it was looking at what I was
it
working
knew where
on,
to
just all of a
go,
sudden
or
it
was it
disappeared.
already, was it freshly killed?
Well, I think there was a rustling in the brush, like it was after something, and it came back and offered me a rat,
So I probably heard something with better ears, I guess they have better ears.
Yeah, their ears are definitely a lot better than mine. When you ever watch the cat or dog, you see the ears pivoting around, just like little radar antennas,
Well, that was the solution, to turn your antennas.
Maybe that was it.
And then you'll get your reward.
Yeah, there we go.
Or maybe it was just showing you it was superior to whatever you want.
It's hard to tell.
I was the longest trip I spent with a guy who said
Well, that's definitely a good shot, as if it understands it.
Yeah, that was just a perfect no-lead slide. I mean, the cat was out there poking at it because there was a tone coming out of the speaker. And, I moved the antennas from the cold to hot, so the pitch changed, and that was all the time the cat wondered what's going on. There's a constant pitch antenna, but if the pitch changes, it's got to go investigate. I did that, and so I go over there, and I had the camera there, so I just, or the cell phone, so I just grabbed the phone, moved the dish up and down a couple times again, it was there, snapped.
Right.
Like a recycle box, it has a few extra holes here and there.
Yeah, the guy sold it.
I can't remember if you said you had a book or one of the books
If you got anybody to call the troops together, we're ready to start.
Start talking.
We ready to start here?
I was going to say, it's about time.
Yeah, the clock says it's time to start.
What'd you say?
Excuse me, Skip.
started at 20 after. Okay, that one is about 21 after. Oh, he's not out there.
Do it. We're here.
The important people are here. Is that right?
Those that count are here.
That's right. Those that can't count are also here. Warren? Comes after that? Okay, well, clock says it's time to get started here. So, talking about my IBT processor, basically a replacement for the satellite finder. And we can see there's my lab assistant, Stripes. Stripes is a little lacking on math skills, but oh, he claimed it, yeah. The little black cat looks like it owns the town, the concrete block. They do that. That's bad. Yep. The good news is, we're on the first one. Okay, so we're together. So anyway, as I was saying, that's my lab assistant. Very strong on curiosity and always wants to be very helpful. Can learn a little more about mathematics and circuits. Anyway, first, what's the IBT? I think we all know what it is. It's the demo radio telescope, and it's our really good education tool. Not really a scientific instrument, but big limitation on what it can do is lots of times the satellite finders we can get a hold of. So I'm going to talk about that a little bit. Well, first I'm going to talk a little bit about the possible sensitivity of something like the IBT. You take the little equation that comes from Krauss's book there, and take a T system of 30 degrees Kelvin, which supposedly some LNBs you can get on eBay get below 30 degrees Kelvin. Who knows if it's true, but anyway. And say 100 megahertz of bandwidth. We're actually going to have somewhat more, but you get some slope from cables and other things, so it reduces effective bandwidth a little. Say, okay, 10-second integration, and the RMS noise that we're going to get, our variation in our baseline is going to be 0.95 millikelvin, so roughly a millikelvin. And I say, okay, we got a dish, it's a half-meter dish, so I'm playing with the smallest satellite dish you can get here. And give it 60% efficiency, they're probably slightly higher than that. But that turns up an effective area of about 0.12 square meters. So throw it in the formula for flux density, 1380 times 2 times TRMS divided by the area. Now it comes out to be about 22 Jansons is going to be my level of fluctuation there. By the way, the 1380 comes from Boltzmann constant, which is 1.38 by 10 to the minus 23rd. And in the formula for definition of Jansky, it's got a 10 to the minus 26. So when those are together, it gives 1.38 by 10 to the third. And the by 2 is because I'm only have a single polarization there. Okay, this came from Krauss. Now, I did have one odd thing in this graph here that I'm trying to make sense out of, because the thing over here is flux density in Jansky's. Then he's got sky background, which is extended source. Well, in the case of Jansky's, the things that count is that the source is smaller than your antenna. Once it becomes bigger than your antenna, you're going to put it in terms of temperature and not in terms of Jansky's anymore. So anyway, why that line is there, why it's so high, because obviously we see a lot of things below it. That was a little questionable, but I went on and took a look and said, well, what's out there at what type of levels, and drew a line down that graph. Came out with these things. Sun, of course, is 2 million Janskys plus or minus. These are all very crude numbers, but you have decimal points in the right place. Okay, we got a moon at 60,000 Janskys, KSA at 600 Janskys. And one of the things I said, well, 22 Janskys is the amount of variation we have in our baseline noise. And a signal has to be somewhat bigger than that. So, okay, well, that's a standard deviation. So let's say 3 standard deviations. That leaves us at 66 Jansky, which would probably be the usable limit if we were limited by receiver front end noise. That's typically not the limit. Anyway, I took a look at some of the sources out there. There's a fair number of them that are pretty well up. Even Jupiter could be within range of that. In practice, it's not, but overall. And then another thing that you bump into, well, M31, a little lower. The satellite belt, who knows what you could call them in Jansky's, they don't quite meet the definition. But notice it's at about minus 5.5 degrees. And at my home, the satellite belt's at minus 5.5. Orion is at minus 6 degrees. So I said, well, Orion's out. These other lower ones are probably out as well. And I was wondering, are any of these things going to be receivable? Well, then I took a look at, well, what can go wrong? Well, antenna back lobes or side lobes are going to, noise from the Earth is definitely going to limit it. Thermal noise from clouds, this was put in here later after a little bit of looking. LNB gain drift. If the gain drifts, that's going to definitely change the baseline of the whole thing. And then I took a look at a few measurements on salvaged LNBs that I had laying around, which is what I was fiddling with. And they're all more like 100 degrees K. By the way, there's an eBay factor on noise temperature of LNBs. You take a look on eBay, you'll see somebody selling an LNB that has 20 degrees Kelvin noise temperature. When you go to the website of the manufacturer, you find it 60 degrees Kelvin. I don't understand that discrepancy. eBay obviously knows the correct answer, is all I can say. But anyway, because of that, that says I really need to multiply that flux limit by 3 from what I had before, so that brings it down to very few sources that I'm going to get. And then I took a look, well, what have we got in satellite finders? This guy here is what I got 10, 12 years ago. I just bought it from one of the satellite places. And it has a nice variable pitch output and bar graph display, which is essentially 100 steps because it's two 10-step bar graphs that one will go up like an MSB, the other is the LSD of the number. So it actually works pretty well. With that one, I was able to easily see the moon, putting it on the satellite dish, the 18-inch dish. This one right here, the cheap thing from eBay, $6, $7, something like that. The readings were really erratic, very poor dynamic range. The audio was a variable level rather than a variable pitch, which is a lot harder to follow with your ear. It had a really nice display. It was flat, slick on the display, but the rest of it was pretty well useless. You can line up a dish on a satellite with it with a little playing around, but seeing anything else was a real challenge. This little analog finder that I found actually did somewhat better. The readings were smooth, a little marginal on dynamic range. Did have a variable pitch tone, but the pitch was kind of erratic. And I actually found the cause of that later, and a little Band-Aid to fix that one up to make something more useful for IDT demos. Of course, this thing here was kind of the very preferred thing for that. It's unfortunately no longer available. They were vintage like 2001, that Channel Master thing. Kerry Smith had done a lot of them. Kerry, yeah.
The 1004, which you'll see.
Yeah, but he's used various models of that. And once in a while, it will show up between $25 and $50 on eBay. I have not actually had one in my lab and taken a bunch of measurements on it yet. May borrow Kerry sometime to do that maybe. But anyway, I'm curious what its dynamic range and stuff is. But people in the past have gotten a lot better results than that than the more modern, inexpensive finders. And I said, well, how about a satellite finder? You can get these little boards with an AD8318 IC. There's some with an AD313, which seems to have disappeared. But they're power measurement chips that were made for self-site power control. For the transmitters, I'll take a directional coupler, run it into that. And that will tell the power going into this kind of thing. But anyway, those you can, $12 on eBay, you can buy a board like that. So I got 2 of them for the one that I'm going to blow up. You get 2 of them, that assures you won't blow up one of them, it seems like. Got a couple of Arduino boards, which you can get about $10. You can get a genuine Arduino, I think it's more like 15. But anyway, I thought, well, add a meter, speakers, push button switches, and need some kind of DC amplifier between the detector and the Arduino. So I'll go into it in a minute. I've got a block diagram. read out a linear function in temperature. And that, in fact, is what I did. And I took a look at it. I have an offset with a DC amplifier is added to the 8318 output, and that goes into the A to D converter. So I'm going to do something kind of like when you were a kid, you might have an old car in the box, a refrigerator came in and defined it as a castle or ship or whatever. I'm going to define this offset voltage as being log G. I figure I can do that. Use your imagination a little. Okay, ABC input at that point then, because I'm adding these two together, is going to be log of T, which I did that because, well, it's going to be temperature we're ultimately interested in, and log G, when those two are added together, well, you add logs, it's equivalent to multiplying the two numbers together. In the Arduino software, I take the anti-log of that by the lookup table, so the anti-log of the log of T times G is T times G. So that says that this offset voltage here is actually a gain control. It allows me to conveniently move the gain around to wherever I want it. So it actually works quite well when you actually start using it. Okay. All right, I'm just going to give an example. Let's say I wanted the meter to be 150 Kelvin full scale. Okay, I point the IVT at some trees, so I'm reading about 300 degrees Kelvin. Now I move my offset up and down until I'm at full scale on the meter. Then I move the IVT up a little bit until the meter goes to half scale, so I'm now roughly 150 Kelvin input. I mean, the log detector will be able to convert it to read out directly in power. Okay, then I took a look, well, what am I going to need for a summing amplifier? This is my first shot at the summing amplifier. It changed a little bit. But out of that 8318 chip, you get 25 millivolt change for 1 dB, and it's actually a negative slope. So I get that, run it by a 510 amplifier, and I go into a 5 volt full scale on the A to D converter in the Arduino. So the result of that is basically I have 20 dB of range that it goes over on the A to D converter. And that's actually a little more than needed, but I lived with that to start with for some other reasons discussed later. And because I'm using the PWM on the Arduino, which is a square wave but varying duty cycle, to create my offset voltage, so I needed a filter to filter 2 RCs. Gives a lot faster filtering than a single RC of the same ability to filter out the high frequency noise. It'll get faster settling, basically. And this was to get the offsetting voltage to the correct level for everything to work. So as PWM goes from 0 to 100%, it uses the full range of the detector. Now, audio driver. First thing I thought, maybe the sounds from that detector are interesting. Now, in my mind, people get odd things in their mind. I came along and said, I bet the sun sounds like frying bacon. I don't know why I thought that. Maybe it was an influence of my lab assistant or something. I really just expected the sun to sound like frying bacon. So I had an audio amplifier in there with a speaker and a nice linear, good audio amplifier. Well, it turns out that when you go pointing the IVT at various things, the log detector tends to level things out. And it sounds exactly the same if I look at trees, cold sky, clouds, or the sun. Anything I look at sounds exactly the same. It's a nice, smooth, even hiss. The only thing I noticed had any sound at all different was if you aimed at a satellite, the hiss actually dropped slightly. But other than that, it didn't change character. So that says having a linear audio amplifier is really not of any benefit. We're not going to hear the bacon frying on the sun. So anyway, I said, well, what's the simplest thing? I've actually used this in the past on things both at work and at home where you needed a speaker to just put out a tone. Because if you just want a square wave, you don't really need a linear amplifier. A 222 transistor, filter the sharp edges off it a little bit, a resistor to limit the current, drive the speaker, and that works very well with very few parts. And if you don't like the volume level, you change the size of this resistor here, which will change the peak current running through the speaker and change it. And in fact, there's probably a lot to be said for just leaving it fixed. By the way, did everybody get to take a look at the crude construction of my box? I passed it around. Okay. Yeah, I'm not sure if I should be proud of it or not, but everybody seems to be fascinated with the way things are constructed.
You get passed around, okay.
Yeah.
Okay. you did have the problem of somehow or another you need to get the power for the LNB into the front end of the thing. Yeah, the 8318 has a 50 ohm resistor right across the input. And 50 ohms, it's not too bad of a match to 75 ohms, and it's a fairly constant mismatch loss. So it's reasonable to just let that mismatch and not give me any trouble. But we do need to somehow or another get power to the LNB, but not get into the 50 ohm resistor, which would smoke pretty quick on 12 to 13 volts. But anyway, around eBay or Amazon, you can find little power inserters intended to put power on a coax line. Do need to look for one that goes above 1 gigahertz, because that's the start of the output of the LNBs. They go from basically 900 megahertz to 1.9 gigahertz or 1900 megahertz. So you should get one of these that goes to 2 gigahertz to insert power. But anyway, they're fairly cheap, couple of dollars, and a little shopping around. And then I took a look at the sketch, which to Arduino is not a program, it's a sketch. I said, well, okay, it's a sketch. That's what they call it. If I can call a cardboard box a castle or a ship, they can call their program a sketch. But anyway, so, I've kind of got hardware, and the inner works of the software, drawing the little dotted lines. So inside my software sketch, I've got ADC, the little 10-bitter that's on the Arduino, and I scaled it up to 14 bits by sliding it over. And the reason to do that is that when you sample something at a fairly high rate and run it through a filter, if there's any noise on the input at all, you get more effective bits, and you don't want to kill those by averaging. So push it to 14 bits. Then I have an RC filter, which is or equivalent that's done in software, and that's roughly a 65 millisecond time constant. And that's mainly just to get rid of effects of aliasing when I go to the next down sampling. This originally I ran at 460 hertz sample rate, and I lowered it to 250 later because it fit better with some other things I was working with. It's still a lot faster than my final output sample rate, which is 20 samples a second. And to go into the SkyPipe thing, it turned up that about 10 samples a second was a good number to put in there. So I was down sample one more time there. Inside the digital filter here, the memory in it, it's an IIR filter, and so it's got a filter of memories. And the memory, interesting enough, had to go 32 bits to avoid errors where the time constant changed with level. With 32-bit, there was no effects of that, so that left me a better behaved filter. So 1 byte, and one of the reasons for choosing the 65 milliseconds was that instead of using a multiply in the coefficient for the filter, the coefficient was a power of 2, so it's a shift, because the Arduino processor doesn't have a hardware multiplier on it. So multiply sends it out a bit. You really don't want it at a 400 or 200 hertz sample rate process having to do that. So, and a shift is almost instant compared to a multiply. So that kind of partially drove that. And now I go through my lookup table, which can be turned on or off with a switch, so I can either have a logarithmic or a linear power response. And lookup table was created with an Excel spreadsheet, which I do have on the thumb drive, part of my presentation. And then I went through a second equivalent RC filter, but this one I can change the settings on. And by pushing the switch on the encoder, when I rotate it, instead of changing the PWM level, it moves the filter over these steps. And these steps, again, were all arranged to use power 2 for the coefficient, so that it was simple and, worked good there. Okay, the SkyPipe interface, that came from Jim Sky's website. I hacked it up a little bit to my liking, but he gave me a very good start on that. Then on the thing for the PWM for the meter, well, mechanical meter doesn't have much resolution. I mean, to 1 part in 200 resolution, you'll really be pushing a mechanical meter. So an 8-bit PWM driving it is really not bad. So I scaled the 14-bit data down to 8 bits full scale, jumped to the PWM. So now my data, as it goes from 0 to 16, whatever it goes to at 14 bits, this goes 0 to 256 or full scale. So the meter moves quite nicely. And at first I thought the PWM would need a filter before the meter. Turns out the meter's mechanical inertia is enough to be a filter, so all you need between here's a resistor. You've got a 1 milliamp meter, 5 volt PWM, throw a 5K resistor in there, and I've got it. Now the tone thing was rather interesting. I'll talk about it a little bit more later. And then I let an EEPROM store settings, so my thing, push button to switch the audio, if I pushed it and held it, it would take various settings and put them in EEPROM. And then when you power it up, it gets the settings from EEPROM, so you're not losing your settings all the time. Now, I also ended up having to add a new tone function. There's a tone function that comes as part of the Arduino software. And at first I thought, oh, that's great. I've already got something to generate a tone. Well, it turns out it uses an 8-bit timer. And when you're moving your input along gradually, the tone jumps pitch on you rather than smoothly goes. And after I changed to a 16-bit timer, then it goes very smooth. It's not quite up to silky smooth, but it's pretty smooth on changing. It just seems to glide nicely from one level to another. That does kill the servo outputs, which I'm not using anyway, because the servo outputs on the Arduino board use that timer. So killed something I'm not using, got 16-bit timer, and Arduino code very easily lets you just poke things into timer registers, unlike Windows where you can't really poke at anything. The Arduino is made to poke at things. You calculate a number from your signal level to give the desired pitch, poke it into the timer, 16-bit register, and your pitch changes. How am I doing on time here? I guess okay. All right. Then I had an interesting problem. I did the thing on the moon where I watched the level through the lunar eclipse. And I noticed my readings had a little bit of a jumpiness about them, It still kind of showed me what I wanted, which the moon temperature didn't change much during the eclipse at 12 gigahertz because you're seeing the temperature a little below the surface, is my understanding. So it lags behind enough. So no noticeable change there. But part of the problem comes about that the Arduino uses the 5-volt power supply for the A/D converter reference and also to the PWM reference. Well, if you take the 5-volt supply, you plug the thing into the computer, it takes 5 volts off the computer power supply. And the computer 5-volt supply is quite noisy. It's not a good thing to use as an A/D converter reference level. So this is just a sample of what the noise looked like while I was running the lunar eclipse thing. And you can see there, this noise looks pretty cyclic. And at one point, as a matter of fact, if I took it over the whole record of where I was running the whole eclipse and everything, they just ran as one big continuous file and calculate back, I came up 1.35714 seconds. And if I assumed that was the period, I could go anywhere in the file. And sure enough, the pulse was there. A nice steady pulse, just like a pulsar, And look at it with an FFT, and we'll see why the FFT in a minute. We can see we've got something at the 0.737 hertz, which is reciprocal 1.35 whatever seconds. And the second harmonic and third harmonic of it all showed up pretty strong. And then there's a lot of low frequency noise in here. And those are all a result of power supply noise. Now, I'm going to divert off the thing about semiconductor physics. I like to kind of bounce off the beaten course once in a while. We're going to look at an NPN transistor. Normally people show a picture of an NPN transistor, they just show this is N, this is P, this is Z. When you actually look at the construction of a transistor, the emitter has got a fairly narrow layer of heavily doped N material. The base is fairly heavily doped, but the collector is a very large region relatively and very lightly doped. The advantage of that is it gives the collector a very high breakdown voltage, but it does it at a sacrifice of ability to inject carriers. Well, the emitter of the transistor, because of the high doping density here, it injects carriers very effectively in this region, which gives the transistor a very high gain. So like 23904, you got a gain of 65. Well, let's say we take the emitter and collector and just swap them. As long as the voltages aren't high enough to kill this junction, which is a pretty low breakdown voltage, in fact, it still works as a transistor. However, the current gain is down like 1 or 2. And you wonder, well, why do you want a transistor with a current gain of 1 or 2? Well, we'll see that in a second here. All right, turn up the Arduino has one little bit of nastiness in it there. It will allow you to flip a switch in software, and if you flip that switch, it gets the AD converter reference from this pin instead of from the 5-volt supply. It turned this switch off. But the thing that's interesting, when the first time you use the AD converter, if you haven't set that switch right, it'll take 5 volts, and if I just put a 3.3 volt reference here, the 3.3 volt supply on the Arduino is quite clean. So if you just ran a wire from here to here, well, hey, it would work just fine as long as I didn't make any software oopsies. Well, considering it's me, I assume I'm going to make software oopsies, and I put a 23904 transistor in there. And we'll see what happens with that. Then in normal operation, I've got 3.3 volts, which that supply is pretty clean. I'm now using it for my reference. I could use one of those old 2.5 volt band gap reference diodes and get an even better reference for probably about $1. But anyway, put this transistor in here, and in normal operation, this transistor, it's got a positive voltage on the base compared to this. This is the most positive, and we're trying to pull the emitter up. And it turns out that I've got 100 microamps of current here, trying to deliver 100 microamp here. So the transistor is very heavily overdriven. So that means the voltage drop from here to here is very small, a millivolt or two. So that says I've got my 3.3 volts over here with no problem. Now let's say I have my oops and software. I close this switch. Well, with this switch closed, this is the most positive, so this is effectively the collector of the transistor, and this is effectively the emitter. Well, that leaves the current gain is at about nothing, and the 10K just doesn't supply enough current here to supply any damage here, and the 1.8K, which I put there kind of as a precaution, turned up you can put it as high as 10K, and the 3.3 volt supply wouldn't even know anything happened despite the fact I shoved 5 here. But if we're going the other direction, it's virtually no drop. So that turned out very useful, and I think anybody that plays with Arduino with an external reference on an AD may want to consider that or some similar scheme, unless you are a very careful programmer or like to blow boards once in a while. But it was definitely a frowny face thing. You'll learn about that. Then how do I change the PWM reference? Because that was the other problem. Well, coming out of a computer chip, it's a 5-volt signal here, and that's not changeable. So I took an analog switch IC, it turned up a 74HC4053, because I had about a dozen of them laying in my little stock box at home. So now the PWM just turns this switch on and off, and then this switch switches between the 0 and 3.3 volt supply. So now I've got a 3.3 volt PWM. It's a very clean signal. And yeah, the 5 volt power drives this, but that has no influence. So it cleans that up considerably. Let's do a comparison on the FFT. So looking at the time domain data, which probably doesn't tell as much as you want to tell, you can see that was the original, and the time domain data afterwards is much more random there, to say the least. When I looked at the FFT, you can see those undesired signals, which were coming from the computer power supply, almost totally disappeared. They're far lower than they were. And all this low frequency noise in here, which I originally didn't attribute to computer power supply, went away. So as soon as I isolated my analog circuits from the computer power supply, it behaved considerably better. So it says if you're using an Arduino for any kind of measurement thing, if it's running off USB power, look out, you'll have very noisy conversions, and there are cures for it. Then turn up here now with a DC amplifier version 4. Versions 2 and 3 kind of disappeared in the process of experimenting. But one of the things, because I have the 3.3 volt reference exactly as drawn on the other sketch there, or other little schematic there, there now is a 3.3 volt full scale, so I changed the gain here to make it the same effective scale factor throughout. But instead of, I put the switch here so that it was switching lower levels. So this is the desired offset level here, not a higher level. It has to be lowered with a divider. That means my filter has to have a gain of 1. I had a spare op amp in that dual op amp package, so I put it here as just a voltage follower. Now I feed back here as an active filter, and that gave me the same noise level that I would have had before, but the settling time is about twice as quick. So in other words, I changed the knob to change my offset, and this responds twice as fast to me with no overshoots or misbehaviors. So it's considerably better. So I made use of that op-ed to make a filter. The other thing I was looking at was possibly running a better A to D converter, and I would need a buffered reference signal for that. I've got, we'll talk about on the next slide. So I've already got a buffered signal there to go to my ADS 1015, and run this signal here to the ADS 1015 because I don't need the gain. It has a preamp inside of it. And that allows me to throw another A to D converter on. And with a simple software switch, I can switch back and forth. In fact, in my software sketch, I put something where I power up it sniffs the I2C, and if it doesn't see the A to D converter there, it just runs the normal Arduino A to D converter. If it finds the I2C A to D converter, it ignores the Arduino one, uses the better A to D. And really turned out to be fairly simple to do that because the way the thing reacts, if it tries an I2C communication and it doesn't work, it doesn't crash. It just gives you a flag you can look at to tell that there was nothing there. So I thought they were pretty nice in the way they handled that. Take a look at this A to D converter. Yeah, again, it's in one of those packages. I don't want to try to solder it with my hand soldering. And you buy a little board on eBay. And in fact, I got it from Adafruit, who makes all kinds of odd little pieces. Odd name company makes all kinds of odd little pieces for Arduinos and robotics, stuff like that. But this is a 12-bit ADC versus a 10, so it's only 2 more bits. At first, that doesn't sound like it's worth a whole lot. But there's another thing. It's an integrating A to D converter. The one that's inside the Arduino is a snapshot A to D converter. It grabs a voltage at an instant in time, stores it in a capacitor, and then disperses the charge to figure out what the bits are. So you're getting just a snapshot in time, and anything that happens before or after that snapshot was taken, you don't see it. Whereas this one, an integrating A to D converter, over most of the sampling interval, it's measuring, getting an average. So it gives us some noise rejection. It has a programmable gain amplifier in it, a true differential input, which is kind of nice. And then the I2C interface, which was built onto the Arduino already. And I did have one funny discovery on that. I wanted to do the A to D converter in a loop run by the timer interrupt routine. It turns out the I2C interface cannot be in an interrupt routine. So anyway, I had to put that outside. So the interrupt routine sets a flag. As soon as we return from interrupt, hopefully we're done with other stuff, and it sees the flag and says, oh, run the A to D converter. So it gives a little more uncertainty in A to D converter timing, but not much. And so I couldn't quite do it the way I wanted to. But anyway, on this thing, it was just wired into the board there. VCC at ground, 5 volts ground, the 2 pins from the Arduino. I ignore that pin, ignore that pin, take A0 and A1 and run them to my analog circuitry. The sketch comes along, figures out the A to D converters there. It gets the extra resolution and extra smoothness, which is worthwhile. By the way, I put it as a $10 module. You really shop around the internet, you can find some Chinese copies that are cheaper. But I bought it from Adafruit because they gave me a lot of software help on how to set the thing up. So I figured, I probably owe them one. So I bought a couple of them to play with. And I'm trying to think of. Dish backload noise. I spoke about that earlier. This is a common device. Everybody's seen it. Your dog gets surgery. You don't want to chew it on the stitches, so you put this collar on the dog, and problem solved. Well, there's things where people are worried about electromagnetic radiation getting to their brain, so they put this hat on for protection. So I combined these 2 inventions and made this, which is basically an aluminum foil over cardboard back shield behind the dish. And I was curious, well, how much is that going to affect it? And the thing that had my curiosity going about that is I could go behind the dish with a CFL light bulb and a work light and move it around the back, and I could see my readings change. It said it was receiving something off the back. So, well, how much is it receiving off the back? So out comes the aluminum foil, a little help from these 2 guys, and put it together. That lowered the sky temperature by 7 degrees Kelvin. So that's a pretty significant drop. That also says, at least this particular dish, that it had a fair amount of spillover in there. And for its original application, that was probably an acceptable trade-off. It may have been kind of almost optimal. For a radio telescope, that's not optimal. So trying to work out a better way rather than clothespins and cardboard and aluminum foil to put that back there. So anyway, that's in work, a better way to mount it. But definitely 7 degrees Kelvin is fairly significant. And then the other thing is clouds. I wanted the best at taking pictures of clouds. Seems to, you'd think taking a picture of a cloud would be easy. I don't have it, whatever it is. But anyway, so I just took one real sampling of looking at clouds and temperature change from cold sky versus a cloud. And I went back and forth to the same cloud and cold sky around it, tried several different places, cold sky. Got pretty consistent results. And when I was aiming at the center of this cloud, it was always bigger. And then when I cranked the numbers, there's 4 degrees Kelvin rise due to a cloud. So if you're trying to look for weaker sources there, that's it, you're not going to see it. 4 degrees Kelvin is about the change you see from the moon going through the antenna pattern. So, a cloud can give you almost as much as that, so it's really quite loud. So apparently the water vapor in the cloud is fairly warm at that, like I said, 4K, which is not desirable. It says in IBT, if you're actually trying to measure anything, a cloud can mess you up, even when it's not all that heavy. This is typical of what I saw, just working with it. And I imagine a thicker cloud could be higher. 4 degrees Kelvin, that's a pretty bad penalty to pay, especially considering it's 4 degrees Kelvin that moves around, the cloud blows through it. So you're getting a change in level, which normally, how do you find something in the sky? You either do a drift scan and catch the level changes from that, and the old Gaussian pattern going through your antenna, or you move your antenna on object, off object, on off object, off object. But in either case, a cloud throwing a variable in there is not a good thing. So when I say want any serious measurements, stay away from clouds. Okay, any questions?
So what objects do you detect?
Turned up.
You gave us a prediction, but what's the
well,
results?
it turned up that none of them were in reason to actually detect. I'm working on it. I'm hoping to be able to get there to the point where I can actually detect something other than the sun, the moon, and the trees, and the satellite belt. Well, and people walking by in front of it, cars going down the road. Which, by the way, if you do demonstrations with kids, it's always interesting. If there's a road nearby, you can aim that, and a car goes by, and you see a drop in temperature, it seems like usually. The reason is the car is reflecting the cold sky into your IBT versus looking, when the car's not there, you're seeing vegetation behind. But you definitely see a change from cars, so that caused a lot of fascination. People walking in front of it, looking at clouds, trees, the moon's in the sky, the moon. Although the moon, interestingly enough, if it's near the satellite belt, you will not be able to tell the moon from the background. The satellite belt is loud. If the moon is more than maybe 5 degrees away from the satellite belt is about the minimum to sort out the moon from other stuff. And if it's 10 degrees away, it becomes very obvious, oh, this is the moon that I came on and off of. But the satellite belt, well, the reason we get this thing cheap is because the satellite belt is there and causes all that equipment to exist. So the satellite belt is our savior, gives us a cheap radio telescope front end, and our curse because we have a patch of the sky that's worthless. Any other? Yeah, Gary.
So Bruce, are you wanting to get more sensitivity in the form of going to a bigger aperture?
Yeah, that was, I
think you squeezed about as much as you can out of an 18-inch dish, right?
Yeah, I realize that an 18-inch dish, that other stuff, it probably isn't within reach. I'm going to do some trying. I've had problems with cloudy skies, and I've also had trouble with my lab assistant doesn't like the aluminum foil thing behind the dish, and it's knocked it off a couple of times. But I intend to see if I can actually hear some of the other sources. But from the effects of clouds, and I'm looking for millikelvin changes, and well, a cloud throws at 4 degrees Kelvin, well, that's going to obviously blow it. So I need to be at a time when there's no clouds, and objects not near the satellite belt, not near the tree line, not near anything else. And I'm still trying, I'm hoping to be able to detect something else, but I'm not sure I'm going to get there. The next step is to go to a 1 meter instead of a ½ meter dish, which is 4 times the area. And also the narrower beam width says the signal from a cloud will stay the same because I'm seeing less of the cloud with a higher gain. However, the signal from a point source will go up because I've got 4 times the collecting area. So that says I stand a better chance with a bigger dish. And that is the next step, to throw in a 1 meter dish. However, for demos at schools and things, the half-meter dish is perfect because it's so easy to carry around and everything, and it's good enough to show the effects of, kids waving their arms or walking in front of the antenna, and, all the other games they like to play, which hopefully educate them a little bit on the fact this is in a way, a remote thermometer. But anyway, so the 18-inch is perfect for the demo thing. I think if you want to see anything with it, a 1 meter or maybe even 1.5 meter, dish might be a better, bet on that. So anyway, I'm going to continue trying. There'll probably something in the SARA Journal, on my tails on that. Either you're not getting anything or I actually got something. But anyway, that will go to the SARA Journal later.
That's excellent work, Bruce.
Okay, thank you. And if you got anything to add to it, because I know you have a slide deck. Have I got a couple minutes left?
You know, a beautiful lead-in to my presentation when that comes up. So.
Okay, so you're doing yours
right after Mike.
Okay. So we got okay, good. Because I actually asked them to put ours next to each other because of the connectivity, but didn't work schedule-wise. Okay, good enough.
Up to my dish and,
All right, good. So, thanks everybody.
We got Mike, the General Operations Manager for GBO. He's in his office, so he's here. He's just talking to somebody. I'll grab him in just a minute. And try to have him here a little after possible.
Did you get eye contact?
Yes, I did. I got eye contact. I got it. Hey, look, like, why are you bothering me now? I got 5 minutes or so. Let's get the ADB. You got time?
for Mike?
Yeah. Unless you're using it for
Mike's sometimes better.
I know, but he's not here yet. I'm just saying, just getting it in and ready to go.
One of the reasons I chose that sample is because it's 16-bit and the same thing. It's quite a bit more expensive than a chip. But all the software is driving the same except the couple of setup languages. And so I was thinking of going with that. Oh, wow. And so I kept the sample. I played with the on-board and deconfigured. I ran into things that even though it's a snapshot in time, when you hit the AD converter, it's a period of time before you can get it resolved back. I actually went trying to get the AD converter. I'm sure I'll try that. But if you set your data off the AD converter, then kick the next sample off immediately afterwards, then you can do another process and get that back. So it's fairly that.
So what sample rate did you get?
Mike's in the hall on the way to meet here in just a second.
That's all right, I'll take mine.
Sure. More bits of data you converted. I'm going to come back later. I still want to get something other than the 7 hundred.
Yeah.
Just because a lot of people say it can't be done.
So, question about the details of it.
Yes, I'll do it. I'll look up. Yes.
I always wanted to know the football field that they have.
Well, next is sort of a very important man around here. He's Mr. Mike, Big Mike Holstein. He basically is business operations manager of the Green Bank Observatory. And something tells me he also was the one who led the champion to keep the Green Bank Observatory here. So come on up.
Well, thank you. First of all, I didn't get a chance to welcome you. Glad you're back. Everybody enjoying your time? Good.
Absolutely hot.
Yeah. Well, I do appreciate the opportunity to talk to you a little bit about, where we stand, and I guess you are aware of the record of decision by NSF. Does everyone know about that?
Yep.
Okay.
On the board over here.
Oh, okay. Yes, that's our press release. So, really quick history. The NSF did a review back in 2012 that recommended that they divest themselves of the Green Bank Observatory, well, the GBT. Let's put it that way. And of course, we had already been doing some contract work in the past using the 140-foot telescope and a couple of others. And so we set out on a quest to find external sources of funding, because we knew that's probably where we were going to go with this. And because they stipulated the GBT, it kind of made things a little bit funny on how we were going to be able to handle this. And by 2015, the decision was made, so there was another thing that happened at the same time. NSF only gives contract awards or cooperative agreements for periods of 5 years. So ever since our inception here in 1956, 57, we've always been operating on 5-year terms. We just always have won those awards, our parent company, Associated Universities. Well, and by 2015, that was coming to an end, the cooperative agreement to run all of NRAO, which included Green Bank. So because of the two things that were sort of meshing at the same time, what NSF decided to do was compete the award for NRAO, but because of the GBT situation, they pulled Green Bank out as a separate entity. They also did that with the VLBA. And the VLBA was renamed the LBO, or the Long Baseline Observatory. So GBO and LBO were parsed out of NRAO. There was always feeling that LBO would probably be rolled back in to NRAO, but GBO's future wasn't that certain. So by 2015, Green Bank Observatory was born. We became our own entity, which also meant we had to rebrand everything. So, when you think about it, every piece of letterhead, every pen, every pencil, everything that you've got that said NRAO on it had to be phased out. Green Bank Observatory had to be brought in. So that's what we did. We're still continuing the search for external funding when, again, as things would happen, 2015, I got a call from Yuri Milner. And he wanted to come and look at the telescope, and he had this idea for a project called Breakthrough Listen. Came, visited, a long story about that, trying to find the limousines that he wanted to bring him here. You haven't been to Green Bank before, I can tell. So at any rate, we did that, and he decided, you know what, I want to use the GBT to do this work. So our first full major partner was on board, $10 million over the next 5 years, $2 million a year, really boosted up what we were going to do. Also got some work from West Virginia University, and got some work from the Nanograd Consortium to use time on the GBT. The interesting thing about that few-year period was that NSF was still making very large awards to organizations that needed the GBT to do the work. So I think it was apparent to NSF, they didn't really want to close the facility. They were just sort of up against a wall and trying to figure out a way to do what they needed to do and satisfy the review committees and everything else meant that we were going to go down this path for our foreseeable future. So over the last 4 years, from 2015 up until now, we have been working with them on a proposal on the face of what it would look like for us to operate as our own entity. LBO was rolled back into NRAO, so now the VLBA is back as part of the National Radio Astronomy Observatory. Green Bank is still now we're the only self-supporting facility in what used to be NRAO's portfolio. And we figure that we will be from now, at least for the next 5 years. NSF asked us to put together a 5-year operating proposal. We've done business plans. Back in 2015, we did a business plan all the way out to 2025. They accepted that. As things happen, the government is fairly slow to act. This was supposed to have happened by 2016. Now it's almost 2020, FY20. But because of this divestiture, they had to do what's called an environmental impact statement. So they had to do a complete environmental review of the facility. They had to look at all the options that might be on the table, even ones that they didn't think about, and the environmental impact of those. But it also meant they had to do a historic assessment of the site. So I say all of that as background because that record of decision is really the last step in the EIS process. It's the step that says, out of all of the alternatives that we looked at through the environmental impact statement system and through the historic assessment system, we have chosen alternate A, which is continued operation with external funding. So the record of decision doesn't give us any money. It just lets us know that they have chosen to keep the facility open. We have to continue to find external sources. They are also working to find external sources. But again, in the meantime, on another hand over here, they have already asked us for the 5-year proposal to operate the facility through 2024. And they have told us that if they accept that proposal, they will fund us at a particular funding level. So we know that they're going to fund us 60 to 65% of what our operational costs will be. We've submitted that proposal. They have accepted that proposal, and we are now getting ready to negotiate our cooperative agreement for fiscal year 20, which will start October 1st. So we know that we're on a stable path, and as long as we continue to keep that external money at the level that we need it, things should stay exactly as they sit right now for us. So that's a long, convoluted story about where Green Bank Observatory came from and where we're going. Anybody have any questions about it? Yes?
Yeah, it's an obvious question. Who are the independent sources for the money? Who are you talking to that you can tell us about?
I'll tell you about anybody we're talking to, and I'll ask you to find some more for us. So, of course, Breakthrough Listen, they're still our major partner.
Yeah.
We were contracted with Radio Astron, which was the Lebedev Institute, for a orbiting radio telescope. And they were bringing us a good bit of money. But the telescope was that satellite we knew was dying eventually, because it was actually built in the 70s, didn't get launched until the 90s. And it finally died. And it just did that 2 months ago. So we know we've lost that money. But in place of it, the Nanograv Institute, or Nanograv project, trying to think of the name of the group, it's the Nanograv Physics Center or something at WVU. Their amount of money has been stable or somewhat increasing. And in all honesty, we've actually done better under this scenario, money-wise, than we had when it was just NSF funding. But we've got to make up the Nanograv, or the radio astronaut money. So there are a couple of groups that NSF has been looking at, and one of those is the Naval Research Lab, NRL. I can't tell you a lot about it because NSF has been kind of keeping that close to the vest. We don't know if they want to use a telescope. We don't know yet which telescope they want to use. We don't know if they're even going to use a telescope. We had been talking to a group with the Department of Defense, Naval Research Lab, whoever it might be, about wanting to use the facility, the site, as a neutral place to work with their contractors. The situation there is that a lot of, let's say, DoD agencies contract out their work to civilian contractors. Civilian contractors, though, have foreign nationals that might be employed by them. Foreign nationals can't go to DoD facilities. So if they can find a neutral place like Green Bank, then they can come here for 2, maybe 3 weeks at a time through the year. And their contractors can come here, and then they can do all of their research work, and they can do testing and do things like that. We can help them fix things as they need them fixed, if that's what they want. And then they can go home. That doesn't take any telescope time whatsoever. We'd be, all good with that.
It's the thinking outside the box model.
Yeah, we're definitely thinking outside the box. We've gotten a lot of EPO money through our EPO group. Again, a lot of it's NSF money. They did a program called Includes. It's a nationwide program. It's sort of a first-gen program, if you've ever heard of that, for first-generation college students. So it's people who, their parents didn't go to college, they're trying to prepare students to go to college. West Virginia received one of 4 grants nationwide. It's going to work through all the colleges and universities that are partners with that program, but Green Bank Observatory is the lead agency. So our EPO group is going to manage all of the coordination of the program within the state of West Virginia. So yeah, we're doing other things. Yes, sir.
Did Green Bank participate in the New Horizon telescope?
We did not. The one that did the black hole work?
Right.
Yeah, we didn't. They didn't, see, I can't remember what it was. It wasn't because we weren't willing to, and it wasn't because they weren't willing to use us, but there was something about the positioning or the spectra that the GBT just wasn't the proper telescope outfitted for what they wanted to do. We've done a lot of NASA work, mostly with space missions. If you may remember the Cassini-Huygens probe, we did work on that. We've done some test bed work for them for JPL in other planetary probes. We were the monitoring station for the probe that landed on Mars. We found Voyager for them. That's well outside the solar system, you know, it's the farthest man-made thing now. So they've asked, NASA has come and asked us to do some things for them. There hasn't been very much money that's followed that, because NASA's kind of a tough nut to crack. If they give money to somebody else, it's money out of their pocket, so they don't like to do that. But we think we're on a track to start doing some work for them as well. And we do a lot of asteroid work, near Earth objects. Yes, sir?
The 385 footers, are they gone? Could they be resurrected if anybody came up with the money, or?
They can, and I'm a little curious about NRL. They may want, for years, for about a 10-year period, the USNO used the 85 footers on a regular basis. USNO now is also using, at this point in time, is using part of the VLBA for part of their work. So I'm wondering if they might want to be using the 85 footers too. There would have to be some retrofit. 85.3 is really the only one that we could probably turn on right away. 85.1 and 85.2 would probably need some work to do that. When USNO quit using the interferometer, 85.3 was continued being used by them for pulsar research. But then they switched over to the 20 meter, which was newly built in 1994 because it had such a huge slew rate, very quick slew rate. That antenna is actually an 18 meter Black Widow DoD antenna that was retrofitted for radio astronomy work. So it is the quickest antenna we've got on site. Another possibility is radar work. We do a lot of bistatic radar work, especially for the near-Earth objects. But right now we use either a radar signal that comes from Arecibo or from Goldstone, and we receive the signal here. We're thinking of putting a radar system here that we could control, either here or somewhere close to us. One of the options is looking at a new telescope site, maybe up in Randolph County, where we could build a small telescope there that has the radar capability and it's shielded away from us, and then we would use the signal coming off of that. So there are a lot of options that we're looking at for those things. Yes?
At one time you had a antenna that was rigged to monitor the sun.
Mm-hmm.
Are you doing that still?
No, I don't know if it was just that the funding dried up. This would have been mid-90s. Certainly the scientist who was primarily working on that moved on to other things. But that telescope is still here. It's the 45 foot. And it's actually still rigged for solar, as a solar burst radio spectrometer. But we don't, actually that telescope now is going to be used as part, you heard Maurice talking about HERA. Well, the HERA prototype antennas were built here. And so we did all the testing for those to ensure that they worked and did all the break-in commissioning. And then they took this design and moved it to South Africa. We did the same thing with the paper antennas, the paper project, which was the original precision array for the probing of the epoch of reionization. So those all sat in the Galford Meadow and are still being used. They all got moved to South Africa as well. Some of them may go to Western Australia. But then the 45 foot is being, the area is being used for another test bed that they're just now getting set up. So, yes, sir, you had something.
Yeah, the vape farm. I heard
Yeah.
rumors about it.
Yeah, I was.
Where
We're trying to.
That's no problem. Yeah, for 10 years, we've been looking at, I need to retrofit the foundation. You know, the antenna's fine.
Yeah.
The receiver room, years ago,
Well, I was out there this morning and I could almost put my foot through the floor.
Yeah.
Probably shouldn't even go out there.
well, it was broken into, it was vandalized
Yeah.
by some kids. So we just sort of fixed it up enough that we could close it up. But I'd like to get that foundation reworked. We cut away a lot of the trees and brush and stuff that was around it.
Is there any way Sarah could help?
I don't know, maybe. Yeah, maybe. I'd certainly keep that in mind. I mean, I'd be glad to share the plans with you. Part of the problem now that we have to work under is the historic assessment. So we have to be, there was a point when this first happened that we were told that basically we couldn't sink a shovel in the ground unless we got approval from NSF to do it. Well, that's untenable when you're doing an operational facility. So we've gotten that relaxed. We do have now an internal environmental checklist that we came up with, and we have an agreement with them that if it's a project that expands to, you know, a certain threshold, that we can do it all internally and just give them notice. If it goes beyond that threshold, then they have to have approval for it. Actually, I keep saying it that way, and it's wrong. They delegated all the authority to the State Historic Preservation Office. So we have to get approval through SHPO to do everything. But all those agreements have been signed now, so we've got another path forward. It's just a little more administration on top of it. So once we go to do that, the key is that if we replace it with in-kind materials, or don't substantially change or alter the structure, then we should be clear to go. But once we still have to get the approved, we have to make that decision to get those approvals, then we'll know what it would cost to do something like that. And it may just be volunteer labor too.
Yeah, with the here.
Yeah. I appreciate that very much.
So do you have any rough idea what the basic foundation work would order of magnitude?
The thing was built on really telephone poles and railroad ties. I mean, that's all it is. And just over the years, they've just rotted and things like that. So what I would really like to do is replace the poles, which were the piers, with concrete. And if I could replace the piers in the same dimensions, you know, so it didn't, hell, I'll even paint them to look like wood. But if we could get those replaced with concrete, then we're just going to replace the ties necessary to support the underbelly of the telescope. I don't think it's moved any. We've supported it so that it doesn't slide, you know, in case it gets any worse. So, yeah, I don't think it'd be too hard.
It has to be realigned because of CAS UP, because, you know, we have a CAS A observation program.
Mm-hmm.
And because of precession, do you think that could be a problem?
I don't know. I don't know how far off it is from when it was originally built.
Well, the beam's still big.
Yeah.
It stays at, its cast A stays in there about an hour and a half, 2 hours or so.
Yeah, so it should be fine.
Well, I mean, it did in the early days.
I mean, you might just have to tweak it a little.
Yeah, it might just need to tweak it, but you know, it was always just a calibration horn. So it was just used for calibration signals. And so if you got it for an hour instead of an hour and a half, you'd still probably get your calibration. But yeah, we'd certainly look at that. We wouldn't do it. I think there's enough play right now in the length of the beams, the ties that it's supported by, that you could move the horn without ever altering the foundation footprint.
I mean, it looks like it's in great shape.
Yeah.
So I'm just suggesting if you come up with a ballpark number and throw it in our direction.
Absolutely no more than $5 million. comes up with it.
Now, as far as, like a Florida university, what are the restrictions on them using the facility?
None whatsoever.
Yeah, well, it's that university in North Korea, they wanted to use it, would they be able to buy time as long as the project was
Well, I'll
verified by
tell
military? or-
You know the FAST telescope in China?
Yeah.
The scientists there spent a lot of time here. During the design phase, we've spent time there. Our scientists have gone there. Our technicians, our our engineers have gone there trying to help them with their RF problems. And they paid really well for us doing that. So, we'd look at any contract possibility, I think. I mean, the thing about Green Bank is, we're the origin site of NRA. And yeah, we're all getting a little older and we're losing some of our institutional knowledge, but as much as possible, we try to pass that down to the people, the newer people that are coming up. And we do really good radio astronomy work. We had a problem acknowledging that because, it's just what we did. But we know we have something to offer. And when you're transitioning from just being the people that do this on a everyday basis and try to keep it to where you're having to sell yourself, it's a really hard thing for people to do. Sure. And so we're working on that. We'd rather not have to do that, but that's the corner we've been painted into, and we're going to try to do it.
Just even during the Cold War, there was a certain amount of work on, radio astronomy and stuff that was done between Soviet Union and U.S. scientists. They seem to say, neither scientists cared about the politics, they just want to look at the sky.
That's exactly right. We try to stay out of those politics. The government is still a government facility. This facility is still owned by the National Science Foundation. So we still have to abide by any issues that come along as far as ITAR regulations, which can be a real pain, but
Sorry, what was ITAR?
International Trade in Arms regulations. Yeah, so think of it like pretty much about anything above 30 gigahertz, that any electronics, anything that's on the ITAR list. So we have to screen people that come in. That's why, for those of you who've been around for a while, you used to be able to walk through the electronics lab. Well, now it's locked. You got to have a key swipe or whatever to get through. That's all part of that security. ITAR is requiring it. So we screen people now that come here for the first time, and it goes through a process, and they say, yep, they're fine, no problem. Actually, we've never had anybody denied. But we have, because we have workshops, international workshops. Sure. But we have had attendees, let's say from Iraq or Turkey or someplace, and they'll come back and say, well, they are from a Part D country. You have to escort them if they're in any sensitive areas. So that happened during the tenure of the Radio Astron project. And when the Russians came, at some point, we had to accompany them while they were working on their equipment, because it was in our same equipment room, the stuff that we had. And so then we figured out a way to put their equipment in an area where the operator could always at least see what they were doing, and we could turn them loose and let them do what they needed to do, because they didn't care. They're already radio astronomers and they're engineers, so there's nothing that we have that they wouldn't know anyway. But the really aggravating part of some of this is, I don't know if anybody has a multimeter, but you know what a multimeter is. That's on the ITAR list.
You mean like the ones you buy at Harbor Freight for
Yeah.
$5?
Yeah,
Well,
yeah.
that's
From
China. Made in China.
So when a film crew comes here, which we've had a lot of media coverage, if a film crew comes here, we have to go hide all the multimeters, oscilloscopes, anything that's on that ITAR list, so that, because you're not allowed to take a picture of it. You're not allowed to film or photograph anything on that list.
So you're
Even though you go to Walmart and buy one, yeah.
But you can't take a photograph.
Can't take a photograph.
You go to Walmart, buy one and take a photograph of it, but you can't take, if it's
Right.
here, you can't take a photograph of it.
That's right.
Okay.
Yeah.
Never mind.
So yeah, it's an interesting world we're living in, but we're happy. We think we're in a good place, and it's certainly a load off of the employees that we have a path forward, and we think we'll be here for a good long time. So yes.
How has the State Historical Society, or whatever you guys call it here in West Virginia, been to work with her, or have you had that much interaction with them?
We had a lot of interaction with them when we were first working out the agreements of what they were going to require and what they weren't, and what, what our operation was going to be. It was interesting. As you can imagine, they don't have a crew of people that know a whole lot about radio astronomy. So learning about the dishes and learning about, the operation of the electronics and because one of the things that they required right off the bat is, and you mentioned the 85s, if you're going to put an 85-foot telescope back into operation, let's say you have to buy a new motor or whatever, it has to be exactly the same motor as the one that's on it. And we said, good luck finding that, So we were able to negotiate through those processes, and because they're scientific instruments, as long as the overall look doesn't change, we don't turn one into a flower pot, and the scientific research capability, is either the same or enhanced, they're going to just give us a green light to do any of that we need.
I'm thinking about the horn, and if we have to move it a couple degrees, sometimes they get real upset if you move something.
Yeah, I don't think they would. If the really hard part has been the houses, the buildings and the houses, because there are something like 41 historic properties on the structures on this facility, as they've determined it, and some of those are houses, and we have one down the site right before you get to the 140 foot, across from the 40. It's the old Beard House. Well, it hasn't been in operation or in use since 1970.
Is that the house where they used to store a lot of leftover junk?
Yeah, that's what we used it for, was storage.
It's got a horn on it.
It had an old horn on it. Believe it or not, they couldn't care less about that horn. All they cared about was the house.
That's because they know houses.
Yeah, about 5 years ago, the back end, which was built onto it to make a kitchen, way back in the day, it finally just collapsed, so it caved in on itself. So for the last 5 years or 6, I've been the one to just tear it down. It's just an eyesore. We got all the junk taken out of it. And I thought, well, we're very community-minded, so one of the things I thought was, well, we'll donate it to the fire departments, let them use it as a training facility. So I'm not quite there yet with SHPO, but I think that, we might get clearance to do some things like that. But I did have to go to every building, every structure, every antenna, every freestanding thing on the site, and I had to have a photographer take historic quality photos. Yeah, different views, different you know, orthos and elevations. And so I've got all of that now, and it's stored away and archived. Yes?
There are a couple of books for the early days of radio astronomy, and I've seen them in previous years at the bookstore and the Science Center, but there are none there.
Oh, is that right?
The one of them was, but it was fun.
Oh, yeah.
That's there. I was there. It was sold out.
There's radio astronomy, but I just can't remember the guy's name. John, he had the big ear.
Oh, John Krause.
And there was another couple of them. They just don't.
Well, they must be sold out then, but we carry those
It's
all.
the time of year.
I've looked for
We're
them
not
on
usually here in
numerous
August,
years.
so
There's
it's
three
the end
of-
of the
None of
season.
them are there.
There's 3 of John Krause's book in the Jansky lab.
Yeah, Krause is out
In the
of print.
where?
In the Jansky library upstairs.
Oh,
Yeah.
well, I was looking for
And
them
you
in
just
the
bought
bookstore.
those,
Well, Krause' book is out of print.
They have that there.
Yeah.
Yeah, we definitely keep those. And
You can still.
since you're
Yeah,
talking
heavy
about
books
that,
down
there's
every once in a while.
as I mentioned, we have a lot of media coverage. We've got a lot of documentaries that
You
have
could get
visited
somebody
us.
to republish them, or you could publish them by the facility or something.
Yep, yep. That's how we did But It Was Fun. We did that. But there was a documentarian who did a documentary called The Wow Signal. And it was specifically about Ohio State and the big year, or Ohio University. But they came here because they wanted to learn a little more about radio astronomy, and you know, we were sort of the same time frame when we started. It turned out that the film took a completely different direction after he'd been here. So we're in it a pretty good bit. He just got a distribution company for it, and so if you hear, you know, you may hear something about it being released sometime soon. And we also have a documentary film crew here right now. During your stay, you've probably seen them.
Yeah, we've seen them.
Yeah, they've been filming here for about 3 years. Yeah. And last year we had 31 media visits. So, you know, for almost 3 a month, either TV crews, news crews. We've been on the Travel Channel, we've been on Destination Unknown, we've been on, you know, so it's pretty impressive to think about a place so remote and out here that we've got that much coverage, but it helps, because I mean, my personal opinion is the more people know about us, the more they hear about it. When they hear something bad, they're going to react to it, so I think it's helped. I know I've taken up more time than you allotted me, so I'm sorry for that.
There's one other thing that we were looking for an accurate description of the radio quiet zone. And there's no such thing. There are pamphlets and brochures that refer to the radio quiet zone, but what are the latitude and longitude
It's in the FCC rules.
SADs? And there was one about a circle of a higher concerned circle around the antenna.
So there are 2 quiet zones. Most people don't know the second, which was actually the first. In 1956, the state of West Virginia created the West Virginia Radio Astronomy Zoning Act. It's Chapter 37A of the West Virginia State Code. My opinion is they probably created it as a move to make sure that NRAO was located in Green Bay, West Virginia. But at any rate, it was the criteria was written by scientific staff, and it protects any radio astronomy facility in the state of West Virginia out to a 10-mile radius. And that's the radius, that's the one that you're referring to.
That's the circle.
That's the circle. It divides it up starting at, I think, 2 miles, and then and it protects against any electrical emission whatsoever. So back in the day, that meant, you know, it could have been anything, motors, electric lines, the whole deal. Then in 1957, 1958, the FCC and the NTIA created the National Radio Quiet Zone. It's much larger. It's 13,000 square miles, basically 100 by 100 or so, a little more than that. The actual latitude and longitude are on our website. If you want to go to the greenbankobservatory.org website, we have an NRQZ section. But it's also in the red book,
That's laid out in the FCC Rule 97.
That's right. And so it protects us against fixed-based licensed transmitters. That's the difference between the two. So again, you think about that, radio stations, TV stations that broadcast back, and again, we're talking about the 50s.
Ham radio stations?
Yep.
Yep, if they're fixed and permanent, then they have to have a license. But now you think as technology has changed, now we're talking, cell phones and Wi-Fi and all this stuff that wasn't thought of back then. But cell phones still have to have a cell tower, and that's a fixed-based licensed transmitter. So that's why you don't have cell coverage here. Kind of an analogous way for me to think about it is the cell tower is governed by the NRQZ, the National Radio Quiet Zone, which is the only one like it in the world. There are other quiet zones, but they're not as stringent as ours. The cell phone itself is governed by the West Virginia Radio Astronomy Zoning Act because it's an electrical emitter. And it doesn't matter that it doesn't operate, doesn't actually function the way it's meant to, it still is an emissions device. And so within the 10-mile radius, that cell phone could be a violator of the state code. So
There is some information in the proceedings.
What I wanted to ask was a brochure that explains some of these details would be very helpful.
we tried to do that on our website. It's kind of complicated to put in a brochure. We've tried to do it on a brochure that we have.
Oh, it's on the website?
Mm-hmm. Yep. We put something like that in our residence hall rooms so people that stay here could understand a little bit about why you need to be quiet. But yeah, I can provide you anything that you want in that regard.
We were talking about historic preservation and the getting good publicity. You ought to get the Barnwood builders down in Lewisburg to help run the Bighorn.
Already called them.
Yeah.
We're wanting to build two, you know, we put up these big white tents that you've seen probably here before through the summer when we have workshops and things and people go out and eat and do things. And I'd like to put up permanent pavilions instead of having to do those tents. And we actually called Barnwood Builders to see if they wanted to maybe, you know, do an episode and build us a pavilion. They do that, but it costs a little bit of money. Okay? Am I
No, I mean,
ready to
you
kick
can
me out?
continue as long as you want.
Oh, hell, you don't want me to.
But sometimes you don't have
Okay.
Where is Mr.?
This is where it all started? Well, they had to be here, I might have stayed. That might have been the first one.
I understand that research that went on here since the early 50s.
How you gonna have this?
This is where it all
What time's
started.
dinner?
5:15.
Well, let's find out what people want to do. I can make this real quick if you want, but, you know.
Yeah, just.
We got 15 minutes.
I can do this in 15 minutes.
We've got 20 officially.
Yeah.
I'm not going to hold you guys. You can't stop my letter such as, you know,
Okay, guys, I always heard of the IBT, and Kerry, you've seen here, has half of what to do with about the IBT, so he made a little bigger IBT, so I'll let him explain what that is.
You can talk a little bit more.
No, it's just, but he says it works pretty good because he's got an analog torch recorder over here, and it works great with kids. So it's a excellent learning.
Can't figure it out. Kid can learn.
Yes, kid
I don't know if it's one or two.
So. You want to put it over here?
Yeah. That's good. No, there were no slides, that's why. Oh, this?
That work?
All right, yeah.
Okay, take it away.
All right, so, once again, kind of a history of how this all came about. And 1998, we had just finished the 408 radio telescope project. Jim Carroll, one of our esteemed engineers, and I even call him scientist, he was really a lot of our, he was a mentor to a lot of us. And he came up with a really cool 408 receiver, and we called it the Carroll Barrel. And it was built in a 4-inch PVC pipe about this long. And the receiver was a superhead, and it was built inside a copper, 1-inch copper tube. And it was kind of it was a strip made up of about 4 or 5 boards. And this thing was incredible. It had a quad-E, a 13-element quad-E antenna. And we had just commissioned it at the 1998 SARA Conference down here in the summer. So Chuck Forrester, another big contributor to our organization, was kicking around the idea of using the little satellite dishes as some kind of a little radio telescope. Wouldn't it be cool if we could use a little 18-inch dish, because it looks just like the GBT, it's an offset parabola. And that really intrigued me. I said, tell me more, Chuck, let's sit down and talk about this. So he said, well, he said, there's the LMBs and the dishes. I said, there's an abundance of them. He said, but we have to build a back end for it. I said, okay. I said, well, I have a friend of mine. This was the gentleman I was telling you about yesterday. He had the graveyard of dishes. Well, he had these nice product 1 meter and 75 centimeter dishes. And I said, I have a source for some nice dishes, but you work on the back end a while. So there was another guy very close to me who was a satellite installation or a satellite TV installation guy. And I used to go up to see him about getting some satellite receivers and things of that sort because I liked playing around with them. And I knocked on his door and I said, Ned, do you have any, I'm up here to get some junk. Do you have some junk laying around? I said, I'd like to take back. I said, one of our members is coming up with this neat idea. And he said, well, I'm having a problem. He said, why don't you walk with me? I think my dish is out of alignment. I go, okay. So I'm going to go out and align my dish. Well, he takes his meter with him, and he goes out and he hooks it up, and he goes, oh man, this thing is off. So he's rotating this thing and shaking it around. He said, and I'm watching this meter, and he's peaking this meter as he's getting the satellite in. And he said, that should do it. And he locks it in. I said, hey, that's a pretty cool gizmo. I said, I knew 2 times out of the year, the sun goes behind the Clark belt and it washes out satellites. So I figured, well, if it's picking up the satellite, it should pick up the sun. I said, did you ever point the dish at the sun and see if it would register on your satellite alignment meter? He goes, why would I do that? I said, I think you just gave me an idea. So I go back home and I find that Channel Master made these satellite dish alignment meters. Excuse me just for a second, I forgot to bring up the clock. And so on our receiver that Jim Carroll had built, the post detector had a VCO, so it would whistle up as it detected energy. The more thermal energy detected, the higher the pitch it would go. And so I said, that's pretty cool, because that's just like our post detector for our 408. So I get this analog meter. This is the one Chuck Forster got, but Chuck, I'm unaware of what I was doing. I take this meter and I hook it up to the dish, and I'm out in the driveway, and I point it at the sun. It pegs. So I pull it away from the sun, cold sky, sun, pegs. I go, it can't be this easy. It can't be. So who wouldn't have thought of this? So I bring it down to tree line level. Trees it's detecting. I said, well, if it's detecting trees, it's going to detect me. So I put it against cold sky. I walked in front of the dish. I said, holy cow, we have something now that we could use a small dish. We can throw this in the car. We have a post detector in here that whistles up, and that's a lot more effective than increasing. Some of the satellite finders have an increase in amplitude of the audio oscillator. So I said, wow. Well, the funny thing about it, I'm out in the driveway, my next door neighbor, so when I was with these guys for like 5 years, and I'm still trying to detect the sun, and I think somebody said, well, Kerry, if you're not detecting the sun, maybe you ought to try a new hobby. I said, no, I'm going to do this. So I'm hooting and hollering in the driveway. I said, yes, I can detect the sun. My neighbor Brad comes over and he says, Kerry, what are you doing? I says, I can detect the sun. He goes, yeah, so can I. What's the big deal? I said, no, you don't understand, Brad. I said, I've been trying to do this for years, and I have something that I think it will really be a great educational tool. So immediately, I give Chuck Forrester a call. I said, Chuck, you got to try this. I said, I have a satellite dish alignment meter, and if you put it on the sun, if you get one with an analog meter, it works like a total power radiometer. He says, no way. I said, yeah, you got to do it. So he does. He gets this model, and he gives me a call back and says, this is unbelievable. So I said, now we have something that we can throw in a car, and we can demonstrate very simply how a radio telescope works. Great educational tool. So this was the meter that I came up with, or found, and it's essentially the same. It's the same. Even has the same model number, but it's a different package. Same circuitry. So it's nothing more than an IF amplifier. Come out of the LNB between 950, as Bruce was saying, 950 to 1450, but they extend up to about 2 gigs. But so this guy is nothing more than an IF amplifier and a detector, and it has an onboard audio oscillator that whistles up in pitch. So what I did is I wanted to make it totally portable, so I put a battery pack on the bottom of it, and then I added a couple features. I had a DC output that could connect to a chart recorder. And then Jim Sky, when he came up with his Sky pipe, I just ran the DC out, the detected output, into his Max 187 A to D converter. It was a 12-bit A to D converter. And he wrote a program, a strip chart program, which worked beautifully. And then after Windows 98, I think it worked up to Windows 98, and that was it. But I understand now Jim has since, I think he has able to work with a USB port now.
Well, you could hook an Arduino to a USB port, which is what I took advantage of.
Yeah.
And that could be in a simpler form than I did.
Yeah. So Bruce did a beautiful job going into the theory of how he went about doing it. I'm more of an applications person, okay? I can modify things, I understand it enough. But I found something I figured this would be a great educational tool. So I knew the channel master meter would eventually go away. I'm going to guess this around when. And this, if you'll see, I think this is the one that has an N prefix. This was for the Navigator program. So it's 98 now. We're developing, this thing's becoming very popular. And then we had a program which we called the Navigators that we tried to kickstart. And then we built 20 of these 18-inch dish IBTs. The original acronym was LBT by Chuck Forster, the little bitty telescope. But it was Sue Ann Heatherly that coined the IBT, the way I understand it, and that stuck, so it's IBT. So what we can do with this thing, I take this to, we have public star watches every month, and while the optical guys are pitching optical astronomy, I take this out and do radio astronomy. And one of the things that's really fun to do, and I know Bruce and everybody who's using IBT, is to have people, when you're demonstrating it, the ultimate high for the kids and spectators is walking in front of it, because it will whistle up. And they love doing that. And explaining to them that you're emitting thermal microwave energy that this instrument can detect. So I also did many presentations for a middle school science teacher we're good friends with. So between the teacher and myself, we came up with this game called Who Has the Hottest Body? And so I'd have the dish outside, and so, okay, we're going to find out who has the hottest body, and this instrument's going to detect that. So the girls are fixing their hair and stuff, and little Susie walks through it, and it registers very nicely when she walks by. And then here comes Big Johnny, and he fills more of the aperture, so it's going to detect more, and it pegs the meter. So look, Johnny wins the contest. Johnny has the hottest body. That's not fair. That thing's not right, And we explain to why, how they fill up the dish and things of that sort. But one more thing that I do with the spectators at the observatory, I said, this is also an alien detector. So, you have to have a thermal signature that this will detect. So if you walk in front of this thing and the pitch doesn't go up, and so I hear the sister and the brother like, you're an alien, I know you're an alien. So I leave him go by. So it's the girl or whoever is saying who's accusing one of an alien. So, little Bobby goes through it and goes, woo, So what I do is I crank the gain back. So it's this flat line. So Susie comes by and it says, this flat line. And then everybody just goes crazy. And his brother said, you're accusing me the alien, you're the alien, you're the alien. So I said, okay, let's just recalibrate here, and then you're okay. So what I can do is I can simulate, because obviously we're around 290, 300 inside. So the other thing I did is I put an audio amplifier in here, so it gives me plenty of audio. I can really crank this thing up. So when they walk in front of it, see, this is my offset. So when they go by, it goes like that. So, and then obviously when somebody is accusing somebody of an alien, they just hear a plateau. But typically, this is what you'll hear when they walk by it. Now, the nice thing about this is I can also take that same DC output and I run it into a chart recorder. So if I have everything set up correctly, so I should have a baseline, and there it is. So when they go by it, so what I do then, I said, well, that's your temperature profile. And right there it is. And usually it's a lot smoother than that. But what's really neat about this is that they can do whatever they want to in front of the dish. So they come up in front and they do all this and wiggle around and everything to get a wiggly line. So then what I'll do is I'll have mom, dad, brother, sister walk through it, and then we keep track of the names. And then we just assign their names to their temperature profile. And I said, this is a...
They get their thermal profile.
And they get their thermal profile, and I put that out. Now we had, I have to get a new stamp, but we had a SARA stamp, and I would stamp the chart recording, and then they'd have the website and stuff. So it's a great educational tool, and it's a lot of fun. And we were down in Washington for the Astronomy Night on the National Mall. And you talk about a potential for outreach. So what did we have, like 7,000 people?
Huge line.
It was crazy. So Chip and I went down and pitched SARA and radio astronomy, and we had an absolutely perfect night. It was crystal clear, and of course, a lot of the optical clubs and stuff are participating in this. But I'll tell you what, had fun with this, had plenty of people in front of it. But Chip had like, the one picture I had of Chip, he had about 50 people lined up for his meteor detection with his SDR. And it's, you know, it's fun. To me, my passion is you know, educational outreach. So when this came along, it was for me, it was a beautiful tool to use, educational tool to use. But when the York College project came along, well, that just took it to the next level. I mean, and beyond. So we're very excited about it. If you have an opportunity, this is a very simple thing to do. Bruce came up with a really sophisticated one. I have, maybe what I'll do next year is do a talk on it. Because the circuit, even, this is the receiver that I built, actually, which I think works better than even the Channel Master. And it uses the 8313. And it works beautifully. So that has some DC conditioning after that, and then an audio amplifier to amplify the 4046 DCO. So it's a great educational tool. As Bruce, I think, mentioned, the small sat finders, you know, it's digital. And then a lot of them are amplitude, they're not even pitch. So the one that you mentioned, I'm kind of curious about.
That one that I really liked the display, well, that display was slick. It was neat.
Yeah.
But it was absolutely worthless. You know, you could sort of find a satellite with a little play-in with it.
Yeah.
But for the radio telescope, it was absolutely worthless.
Yeah, and most of them are. But this here would be in Bruce, if you want to do it. It wouldn't be too difficult to make one.
Are you able to detect anything besides the sun with that?
Oh, yes, and thank you. Yeah, the moon, this particular aperture and my receiver will easily do the sun on the same level as Bruce. But remember, Bruce is he's using an 18-inch dish, so I'm very curious about that. I'd like to see that. But we'll have to hook yours. We'll have to hook yours up.
That's a beater by the half.
And I'll take it once we move it back over into the lobby. I can take it out and we can demonstrate it against cold sky and trees and stuff. And it has some good. I'd say it's about 2-degree beam pattern. So the trees that are out near the dorm, there's a nice gap between them. You can easily differentiate cold sky between the trees. And it's
getting a CFL light bulb out there is another thing. You know, they are hot at radio frequency. I mean, you got ionized gas of close to 10,000 Kelvin inside that fluorescent.
And if we can see the moon without, I mean, I can find the moon, but it makes it easier if you can see it. The moon will be positioned very nicely, so we can show you how to detect the moon with it. It's just about 1/4 after, so.
Do you do any hydrogen?
No. It's at 12 gigs. So this one's at 12 gigs. Yeah. So that's the IBT and pretty much in a nutshell how it got started.
Okay, guys, I want to introduce you to food. There's food in the cafeteria.
No food.
Bring your fork this time?
It was good.
You can still find these on eBay.
intermediate frequency, and
I had my portable.
It's manufactured as a dish line meter. You're welcome. Oh, you can't. I mean, you would have to look. If I would, I wish I would have gotten this. Caudill is the manufacturer.
But I'll come by some way.
I love it. It's fiberglass.
Charles is going to,
Yeah.
Yeah, that's a great one.
Oh, really?
Use this as a force site, and you go parallel right off the house, right off this That's your force site. If I put it, right there,
Good. Do you bring your noise figure meter with you?
It would decide. That's what they would
So these ones have a bias. Probably need to just set up the bias test.
This